welcome to the Greater London Region Design Challenge final. So, as Jelena said, I'm Ben Hodgkinson. I've recently been very honoured to take the role of the Design Challenge Chair. Inherited a great competition from the former chair, David Ball. He's created a competition that can really discover some innovative engineers emerging in the marketplace. So I'm particularly interested in that. My background is in motorsport, in Formula One. So I see the work that you do in the design challenges very analogous to what I do every day as my working life. So I'm looking forward to seeing what innovation everybody can come up with. So I'm also very grateful for the attendance of our president, Terry Spall, and would like to hand over to him now.
Okay, well, Ben, thank you very much for that. And if I could just add a huge welcome to everybody to the Greater London Regional Final of the IMechE Design Challenge. As you just heard, my name is Terry Spall. I am the 135th president of the Institution of Mechanical Engineers, and I do follow in the footsteps of many illustrious engineers. Our first president back in 1847 was none other than George Stephenson, who gave the world the locomotive. Well, his achievements do go somewhere beyond my own, but my presidency comes after a very enjoyable and rewarding 40-year career in the automotive industry, with 31 of those as a chartered mechanical engineer. As I'm talking to an audience of young aspiring engineers, I'm sure you'll be delighted to hear me say that in studying engineering, you've already made a great choice, as really engineers and technologists are in such great demand around the globe because they can really drive a nation's economy. According to data from Engineering UK, 23% or £1.4 trillion of the UK's turnover comes from engineering, and the sector employs 5.6 million people across 720,000 engineering related companies. And it's also a great multiplier. So when somebody gets a job in engineering, it creates another 1.74 jobs elsewhere in the economy. So all good news about being an engineer. But what's also true the world over is that we don't produce enough good quality engineers. And to illustrate that fact, in a recent study, Engineering UK estimated that we'll need around 200,000 engineers and technicians per year for the core roles at level 3 and above in the UK over the coming years. And they're predicting a current shortfall of around 50,000 per year, so that's 25%. So with the supply demand being skewed that way, it inevitably means that engineers will continue to be in good demand. As a consequence, on a positive side, it means that they will also attract good salaries, well above the average. But of course, it's not all about money, is it? Well, maybe it is, but who knows? But anyway, in my opinion, one of the most important considerations when selecting the job really is finding something you really enjoy doing. You spend most of your waking hours at work, so make sure you find something that you find fun. If you can do that, then success will follow you, and you'll always go that extra mile, be that little bit more motivated and that little bit more committed. Well, the IMechE is a global organisation. We have members spread across 140 countries, and more than half of our 115,000 members worldwide are classified as young members, in that they've achieved professional registration in the last 10 years. These are people like yourselves, highly motivated, passionate about their careers, but also want to have a bit of fun as well. So, speaking about having fun, that brings me on to the design challenge. It has been a hugely successful competition, engages thousands of students each year, and it really has influenced many young engineers to go on to great things. As you heard, the competition was founded actually back in 2007 by Dr. David Ball. I've known David personally for many years. He's a hugely experienced engineer and is passionate about the development of engineers, and that's what led him really to create the competition. He created it really because, well, he wanted to find a way to get undergraduate engineers thinking about real-world engineering requirements. So he created a competition where the students had to start from a clean sheet of paper and design, make and test a device to complete a specified task. Now, originally there were 8 tasks developed, and these were later reduced to 4. Well, it's actually the 4 that work the best. The repeatable vehicle, which is the one you've been doing, is a particular favourite of mine actually, as I am a vehicle engineer by background, and I've spent my entire career in the automotive industry, so anything with wheels on really does work for me. I'm very aware of the need to develop engineers who can address real life engineering challenges. And for many, this competition will be perhaps the first time you've had to really apply your taught engineering knowledge and solve a problem in a competitive environment. It will make you think like an engineer. It's designed to challenge you. It's designed to inspire you, and it may at times perhaps just frustrate you, but when things don't work out quite right first time. But you can be sure that you will emerge from the competition as better engineers. You can take that for granted. It will be an experience that leads you on, or I'd say it could be an experience that leads you on to some of the other IMechE challenges we run for undergraduate engineers. If you're not already aware, they include the Railway Challenge, the Unmanned Aerial Systems Challenge, and of course, my favourite, Formula Student. So looking at the team list today, I know many of your universities are already established competitors in those competitions, but for those universities that haven't yet competed in those, maybe you could be the first students that persuade your university that they should get involved and be the first to establish a team and compete. So give that some thought. But just focusing on Formula Student for a moment, I've been very involved in the competition since it started 22 years ago. I was there at the first one, and I've spent many years since as a design judge, and I've also spent 5 years as chief judge. I was also very involved in the establishment of the Formula Student AI competition, which includes the development of autonomous vehicle control algorithms, which is a really exciting development for Formula Student. It's been absolutely brilliant to watch that develop. I mean, Formula Student's seen in the region of 42,000 students from all over the world compete and then go on to some really amazing careers with major organisations who've been fighting to recruit them because they are so employable. And the parallel with the design challenge is the fact that both competitions get the students to work as a team and solve a problem in a competitive environment. The learning process you go through is such a powerful personal development experience, as you need to learn to work as an effective team, to manage a project, to deliver on time and within budget. And you have to design, manufacture and build your solution, test and develop it, and then compete. So this emulates the real life situation of product development really well. So by going through these challenges, you can easily see how they prepare you for your first employment roles and why employers want young engineers to have that experience. It creates engineers who can very quickly contribute and integrate with existing engineering teams, as they've got many of the skills, technical, commercial, project management, and very importantly, interpersonal skills, which they'll need to work effectively with other team members. In the case of Formula Student, most students who've competed have enjoyed accelerated career paths and progressed to senior positions. So the process works, and I hope the design challenge works for you and helps you to become a competent professional engineer. One thing you absolutely must do is make sure that in your first CV you mention you were a design challenge competitor, because people will look at that and they will respect it. And it might well be the differentiating factor that gets you the first job. So if you do get a chance to participate in any of our other challenges, like Formula Student, my advice to you, which is heavily biased from my own positive experiences, will be to absolutely do it. It's a roller coaster experience. It'll take you through the full spectrum of emotions, from complete despair to complete jubilation. And when I talk to people who've done it, they always say it's an experience they will never ever forget. So there's some good things lying ahead. So do look out for these things. So turning to this year's design challenge competition, the regional heats are by necessity really going to be virtual this year, unfortunately. The original physical competition that David Bull envisaged is not going to happen at the regions, but hopefully it will when we get to the final. But the move into the virtual world in so many ways has, in my view, enhanced the competition. It's further stretched the learning process and allowed you to broaden your skill base in a manner that also gets great relevance to real world engineering design. So my thanks to the Design Challenge organising team who've managed to adapt the competition. I have viewed the webinar that explained the use of the new app. I was really impressed to see how much of the competition has been successfully transitioned into the virtual world. So particularly thanks to Professor Tim Baker and his team for developing that for us, to keep the competition alive during the pandemic. As well as being a learning experience, it should also be a fun experience too. So I hope you've enjoyed your experience of the competition thus far, and I hope you'll enjoy what's going to come today as well. So whether your team emerges the Greater London region winners or not, the fact that you've been part of the competition means that you'll have taken huge steps towards becoming competent professional engineers, and I hope you do feel that way when you reflect on your experiences of having been a competitor. For the winning teams, the national finals await, and this will take place in October and will hopefully be a physical event at our headquarters in London. And by that time, I sincerely hope, and I'm sure you do as well, that we'll all be talking about COVID in the past tense, but that remains to be seen, so we'll see how we get on. So finally, my thanks to everyone in the Greater London region who's contributed to this event. My thanks also to Janina, Helena, Christina, and the IMechE staff team behind the scenes for delivering the competition so professionally. But also, and most importantly, thank you to our competitors. It is an extracurricular activity. You don't need to do it, but I hope you feel it has been time really well spent, and it will be the start of your future association with our institution. You know, we can support you at every stage of becoming professionally registered. We can help you throughout your career. The more you get involved, the more rewarding you'll find the experience. And I say that based on my own career-long engagement. So that's all from me. Good luck to you all. Enjoy the experience and have a great competition. Thank you.
Many thanks, Terry. I think that's the point where I take over. So thanks for your words. Welcome to everybody. It's been quite a task put everything together for this morning. Lots of people helping behind the scenes. So I'm going to kick off with just a brief outline of the day's events, and we'll take it from there. So fingers crossed that everything is going to work okay. First things first, can you see my slides on the screen okay?
Yes.
That's good. Okay, so first thing I would like to do is an introduction to our judges. I'll come to that in a moment. Then teams will be ready. We've got lots of you on the call. Teams will be ready after we've welcomed the judges. What we're going to do is a 60-second introduction to each of the teams. I'll pop up the posters for you to be able to see, and just give. Probably best if it's one of you, or if you've already got it scripted and you're rehearsed, then for sure others of the team can join in. But we just want kind of like a bit of speed dating meets engineering. Just say hi, hello, and your poster will be on the screen as we do your introduction. Then we're going to move to the presentation competition, which involves the top 3 teams, which obviously a lot of the judging has already been done behind the scenes. And so we will present the videos for the top 3 teams, followed by the Q&A for those top 3 teams. After that, what we'll be doing is what we've realised. I was working with Ben last night, Ben Hodgkinson, who you'll be introduced to in a moment, and I realised that the timings, we're quite used to having lots of sort of setup time for the devices and so on, but what we're going to be doing is just running a series of essentially videos that show the virtual heats with all the teams and all the devices running. So that frees up a bit of time, and one thing that Ben suggested was it would be nice just to show the CAD of the devices, so that he's got a few questions for the teams. It's not going to influence the scoring, that aspect of it, but it gives us the opportunity to show all of your amazing work. Just while we're at that point, by the way, I just want to say I'm so impressed with the level of submissions that we've had, the CAD data, the bill of materials. This is the first time we've put it into the competition, and there was a bit of apprehension because we've not really done anything face to face, and you've done all of it remotely with the occasional webinar to help you, a lot of it written instructions. As I say, really impressed to see the level of work, the level of detail, and to prove that as year 1 students you're able to pick something up as sort of complicated as a bill of materials and make really good sense of it. So you know, well done to everybody involved. So after the design competition review, we'll have a look at the leaderboard heading into the virtual competition. and then we'll be back onto track, which Jelena will be relieved to hear. We'll get onto the virtual competition, and we'll run those live, and you'll see what's happening before your very eyes. So I'd like to welcome the judges for today, starting with Professor Ben Hodgkinson. So Ben is chairman of the IMechE Design Challenge competition. He's also recently joined Red Bull Powertrains as the technical director. So Ben, do you just want to say a quick hi and hello?
Yeah, hello. As per my previous introduction, I'm Ben Hodgkinson. I've been at Mercedes designing their Formula One engine for 20 years, and like Tim says, I've just been asked to be the technical director of Red Bull's new venture into creating their own powertrain. So very much looking forward to that.
Thanks very much, Ben. Then next we've got the head judge, Davide Migliorini. Davide, would you like to say a couple of words?
Good morning, everybody, and thank you again for all your work. I'm Davide. I'm the engineering team leader in Aerostech, where we make mainly fuel cell electric turbo compressors.
Thanks, Davide. And then next on to Captain Tom Cheshire, who's deputy head judge. Tom, would you just like to say a few words?
Good morning, everyone. Tom Cheshire. I'm a career naval officer, and for the last 3 years, my role's been as the chief engineer in the nuclear propulsion team in the submarine delivery agency. So, nuclear reactors and how we power submarines is my business, and looking forward to the day.
Excellent. Thanks very much, Tom. And Stephen Parkinson. Stephen, hi, are you there? You're able to give us a few words.
Hi, everybody. Yeah, I'm education manager for Autodesk. Autodesk is a company for people who make things. In the mechanical engineering world, you may have used some of our products, and I'm looking forward to seeing all of your work today.
Excellent. Thanks very much to all of you. So, the judging panel. So we met the judges, and this is just a quick resume of what we're going to be going through. So Davide and Tom are doing the poster and presentation competition. So they've done the scoring of that. Ben is doing the design competition, and then collectively all of the judges will be contributing to the Q&A for the presentations for the top 3 teams. So we're going to move on to the team introductions, and I'll just give you 30 seconds teams just to digest the running order there. So Brunel, you'll be first up. You'll have a few seconds because I've just got to swap presentations to get the posters on the screen. So we'll have Brunel, followed by the 2 Durham teams, followed by the 2 Kingston teams, followed by the UCL teams, and last but certainly not least, Hertfordshire. All right, so the way this will work is I'll pop your poster onto the screen, and then if you can, we're not running it exactly to the clock. There's no penalties if you go over the 60 seconds, but we don't want to be here at 2 o'clock this afternoon still suffering because teams were taking 40 minutes to introduce themselves. Okay, so let's keep it short and sweet. So just give me a second to swap presentations, and we can get started. Okay, quite large files, some of these, so it does take a little while from time to time for them to open. There we go. Okay, Brunel, just loading the slides. Brunel, are you there and are you ready?
Yes.
Hello.
Okay, good. Brunel, can you see your slide on the screen?
Yes, we can.
Great stuff. It's the floor is yours. Go ahead.
Thank you. My name is Antonio Ventura. I'm an electrical and electronic engineer.
Hi, I'm Matthew Chia, doing civil engineering.
Hi, I'm Alex Danieli, and I'm doing aerospace engineering.
I'm Tudor, and I'm doing automotive engineering.
So this is our project. It meets all the requirements for the competition. Here we decided to go with a little bit of PLA for sustainability because it's a biodegradable plastic. And we decided to go with this X design because of it makes the robot lighter because it has less PLA, and it also gives a sleek design, I would say. We decided to go with the gear mechanism because with gear ratio to make the switch to go off and off the motor. Yeah, we decided to join a little bit of mechanics and electronics as well to make the robot more diverse, I would say, in the various parts of engineering.
Okay, excellent. Thank you very much. That was pretty good on the timing. I have actually got my stopwatch out just in case. Anything else to add, Brunel? Thank you very much.
Thank you.
Great stuff. Good. So next we're moving on to I've got Durham. Looks like I've got Durham 2's poster up. It says at the top. I was expecting that to be Durham 1.
I can go if you want.
Sure.
Good morning, everyone. Let me introduce you to Team Incompressible. Our vehicle uses a lead screw mechanism to actually return our vehicle to the origin. The lead screw rotates at a reduced RPM compared to the motor, allowing only a small section of the lead screw to be needed. Our front board maximizes the range of impact angles, which would activate the latching push switch, and it also cushions the vehicle on collision, which reduces the force induced on the container. Large wheels were used to maximize the distance per rotation of the motor and gives the vehicle a better ground clearance for non-ideal conditions. Our vehicle is easily repeatable and only requires 2 switches to be pressed for it to be ready to run again. And we had sustainability in mind when designing our vehicle. Therefore, nearly all of our parts are recyclable. Thank you very much for listening.
Excellent. Thanks, guys. Thank you very much. Durham 1, here we go. You're up.
Hello, everyone. We are Durham Team One. Our design is a 4-wheel design with a Dpdt Switch at the front for reversing direction. We use a lead screw method for measuring distance. As the vehicle progresses, the bolt moves along the lead screw, and then, of course, as it reverses, it moves back. This is very important in measuring distance correctly. We have used a large motor, and our design is very precise and accurate through this lead screw method. Our gear ratio is set so that the lead screw moves a large distance along the wire for precision to accurately return to the original position.
Excellent. Thank you very much, Durham 1. Okay, next we should have Kingston Team One. Are you there?
Good day. We're Team Uller. My name is Matthias Weiler, and together with Nick Sagadinios, Nathan Wingfield, Sukta Sohal, and Atif Farooq, we are one of 2 teams representing Kingston University. Over the past months, we have designed a 3-wheeled, 3D printable, repeatable vehicle, which is called cheap, simple, and reliable. By using 2 gears and a simple circuit, we have created a way for our vehicle to measure the distance it drives and return to the same point as it started from. As a team, we have enjoyed working on this project and are happy to have gotten this far in the competition. And we're looking forward to tell you more about our device, and thank you for your time and attention.
Excellent, that's great. Thank you very much. So, on to, this should be Kingston Team 2. Are you there?
Hello, good afternoon.
Hi, it's all yours.
Wonderful, thank you very much. So this is our design that we have worked on over the past months. It utilizes a Dpdt switch, which drives a mechanical braking system. So pretty simple. Just drives a shaft, drives a thread. Very mechanical. Very mechanical. Yeah, it's pretty simple system. We would like to say on behalf of the team that we are a team of excited engineers who have taken this opportunity to learn above everything else. And it has been such an opportunity to learn. So thank you very much for this opportunity.
That's great. Thanks very much, Kingston Team 2. So I've learned how my PowerPoint's working now. As soon as I touch the screen, it progresses to the next slide, which is what caught me out earlier. Okay, I'm back in my comfort zone. So UCL Team A, hello, are you there?
Hello, we are Team Analog from University College London.
Hello. The particularity of our car is that it uses a cassette to measure the distance mechanically by reading out and reading in the state.
Dpdt Switch is used to change the direction of travel after inputting the code.
And we use MATLAB to quantify the performance of the car and the developments that we needed to be made.
Generative design and FEA were used to reduce the weight of our wheels and chassis without sacrificing strength.
Thank you, and we look forward to a good day of competition.
Good, thanks very much, guys. Thank you. And swiftly moving on, we have UCL Team B. Are you there?
Hello everyone, I hope you're all feeling well today. We are a team of 5 students studying mechanical engineering at UCL, and we're glad to be part of this competition today and to finally get to share our design with you all. We call ourselves the Incredibles, which comes from our the vehicle's notable not-in-thread distance measurement mechanism, which we consider to be the defining part of our vehicle. We have been working hard to optimize the vehicle's performance by making it fast, stable, accurate, and precise, while staying within the limitations of the competition. We even built a real-life prototype that helped us know what adjustments we needed to improve our design and to make it run as smoothly as we wanted to. Our team is proud of the design outcome, and we enjoyed undertaking this challenge, which allowed us to learn many of the engineering principles we wouldn't have known otherwise. Once again, we are thrilled to be here today, and we're excited to see how everyone approached this challenge.
Many thanks, UCL Team B. Hertfordshire. Hello, Hertfordshire, are you there?
Yep, can you hear me well?
Yep, we can hear you. Welcome.
Hi everyone, we are the University of Hertfordshire team, consisting of Archie, Kirsten, Matt, Ryan, and myself, Anthony. We managed to design, develop, and build our repeatable vehicle in the short 2 weeks we had available to us. Our vehicle makes use of a mechanical distance counter, being a screw and nut that will stop the vehicle at the origin upon its return by activating a kill switch. We designed our vehicle to have a low center of gravity and small frontal area in order to increase the stability and reduce deviation. Our powertrain consists of a 24-watt motor, powered by 4 AA batteries, which is connected to a gearbox with a ratio of 1 to 104, giving us a final output speed of approximately 215 RPM. The total price for our vehicle was £28.05, and in order to meet this tight budget of £30, we used cheaper materials and construction methods as a result. Thank you for listening, and we hope you enjoy our submission.
Excellent. Thanks very much, Hertfordshire, and many thanks to all of the teams. That was I enjoyed that. That's really good. It's a nice way of introducing everybody and getting a snapshot of the incredible work that you've done. Okay, so we're going to have one of my awkward pauses. I'm just going to stop sharing, and I'm going to have to go to another file, and then we're going to be ready to start looking at the posters in a moment. Just talk amongst yourselves if you can. Okay, Yellen, are you there to be ready for the poster presentations? So sorry, for the presentation competition.
Hi, we're ready.
Okay.
Just a moment, and Natalie will start playing the presentations. Natalie?
I'm just going to announce who the top three were. So.
Okay.
Yeah.
Go ahead.
Yeah. Okay. Okay, presentation competition. So what's going to happen is the top three teams, we are going to present their videos, and then that's going to be followed by a Q&A session with the judges. So the bit that you'll be interested to see is who are the top three teams judged up to this point. And in no particular order, the three teams where we are going to be presenting their videos for all of us to watch, followed by each team having a Q&A. We have Durham 1, UCL-A, and UCL-B. So congratulations to those three teams. We're going to show your videos. Obviously, you'll have a few minutes to be warming yourselves up for the questions. So Jelle and Natalie, over to you.
Just as a note, we are going to show the UCL-A video first, then Durham, and then UCL-B. Natalie, whenever you're ready. Thank you.
I don't think there's any audio. Can you replay it again, please? Oh.
Yes, we can't hear anything.
Hello and welcome to Team Analog's presentation for the 2021 IMechE Design Challenge.
For the 2021 IMechE Design Challenge, our task was to design a repeatable vehicle that would drive up to a wall and then reverse to its start position. During scenarios 1, our design focused on the accuracy of drive, and you can see our design in this image. However, for this scenario, we have aimed to minimize both the time taken and energy used to complete the run. This must still all be done by a vehicle costing less than 30 pounds and smaller than 400 by 400 by 400 millimeters.
In both designs, distance is measured mechanically by moving the tape from a full reel onto an empty reel. When the vehicle contacts the wall, a Dpdt switch reverses the polarity of the motor, sending the car backwards. As the car reverses, the tape then travels back until it reaches its start point, where a strip of foil adhered to the tape contacts two wires, which complete the circuit that stops the motor. After consideration and physical testing to check the validity of the idea, we chose to use a cassette tape rather than build our own reels, as a cassette fulfilled all of our requirements, including strength. In order to bring the vehicle back from the wall, we decided on switching the polarity of the motor. This will be done by using a Dpdt type button switch located in the front of our model, which will be activated once the vehicle collides with the wall. The collision won't cause any damage to the switch, as our team determined that it can withstand a force of over 40 newtons, far greater than the calculated 3.75 newtons from the collision.
Thanks to the simulator, we managed to study how different parameters affected time and energy. Firstly, we saw that reducing mass, especially rotational mass, led to smaller energy consumption and improved times. We also confirmed that decreasing the gear ratio would vastly improve time to the expense of little extra energy. The simulator also allowed us to determine that the spring constant had a negligible effect on energy and time. To further determine a gear ratio, we analyzed the speed values given by the simulator. We checked using our own MATLAB impact simulator that the G-forces experienced at impact didn't exceed the previously calculated maximum.
To reduce mass, the first step was to use nylon nuts, bolts, and washers instead of steel ones, saving us more than 61 grams. Changing from steel to carbon fiber axles further reduced the mass by 32 grams, and a big redesign of the laser-cut chassis was completed to remove unnecessary material. In total, more than 200 grams were saved.
Simulator testing showed that reducing inertial mass was very important. To minimize the wheel mass whilst ensuring adequate strength, generative design was used, which utilizes finite elemental analysis to identify areas which can be removed whilst causing minimal structural disruption. The additive manufacturing process was inputted as a consideration into the Fusion 360 simulation so that the design is suitable to manufacture given the layering process of 3D printing.
The light and chassis design was studied with finite element analysis to understand whether the new design would still be strong enough after the changes made to it. The results showed that the structure was suitable and that the maximum displacement of any part was less than 0.5 millimeter.
The alignment system was identified as an area of improvement after the first scenarios week. A laser is used to help line the cars up straight with the track by aiming the laser on the center of the targeted wall. To improve the alignment of the car as it runs down the track, the steering angle of the front axle is adjustable up to 10 degrees, so can be varied to account for any observed deviation.
We have increased the length of the vehicle to the maximum allowed length of 400 millimeters, with a boom to reduce the distance it needs to travel. The gear ratio has also been modified so that the car can travel faster.
Using the pricing system from the IMechE, we found that the total cost of materials for the vehicle is £26, and excluding parts less than 20p, it is £19. From 3D printing our own wheels, we saved £7.96, which allowed us to pay for lighter materials such as carbon fibre axles and nylon fastenings.
Furthermore, we wanted to compare the simulation results with our own MATLAB code. We had a small 370 millisecond difference regarding time and a 0.2% energy difference. The simulated speed was 0.04 meters per second different to our expected value. These are all small differences, which leads us to believe that our own code is a suitable model. Yet we know that our model provides us with vastly more information, such as RPM, impact forces, and acceleration.
In our final results, we can see in the above graph that energy used increases mostly linearly, with a jump in the middle whilst the collision is happening. At the bottom, we have the graph for acceleration during the collision, which reaches over 20 meters per second squared, which our MATLAB model showed us was low enough that the car would not skid. In the end, this brings us to a total runtime of 9.23 seconds and 0.61 joules of energy used.
Thank you for listening to our presentation, and we look forward to your questions.
Many thanks.
Hello, and welcome to our IMechE Challenge presentation. We are Durham Team One. The key aims. Measuring the distance the vehicle has moved correctly is vital. Therefore, an accurate mechanical measurement method is needed for success. We must also remain within the £30 budget, and the vehicle must be easily and precisely assembled within the Durham University workshop. We had 3 initial design sketches. All 3 designs had 4 wheels with a Dpdt switch at the front for switching direction. The first 2 measured distance using a thread wrapped around a drum. The final sketch measured distance using a lead screw design.
For our final design, we used a threaded rod as the most accurate and durable option. We used an acrylic body as this was the cheapest option and is easily cut and glued in the workshop. We used a 1 DC motor as this significantly cuts down the price. And we used 4 big soft rubber wheels as these give the best durability and have a high coefficient of friction. They have good grip so the robot doesn't go past the endpoint. This is our final design's drawing. We used finger joints because they can be used to easily slot the parts together and makes it easier to replicate the CAD model when built in real life. They also help the vehicle to go in a straight direction as everything is positioned precisely. We also used gearing between the driven axle and the lead screw. This means that the nut travels further along the lead screw and is therefore more accurate. This is our circuit diagram. To begin motion, the first switch is pressed. When the car touches the wall, the Dpdt switch will reverse the motor polarity and the car will go backwards. When the car reaches the start point again, the lead screw nut will stop the motion by pushing the switch. For our risk assessment, we thought the main 2 hazards were acrylic or laser cutter fumes, which can be prevented using a good air ventilator. Also glue and soldering burns, which can be prevented with good training, gloves, and a clear workspace. This was our risk assessment as a whole.
This shows a simplified view of our bill of materials. Key to note that the mass total 1.3 kilograms and that we're within the £30 budget. With regards to the lead time, most of our parts should be coming within 1 week, which means we can assemble most of the robot quite early, and the last 2 parts should be coming within 4. With our calculations, we found that the maximum stress through the axle should be 40 megapascals, which gives us a factor of safety of over 6. We have 120 seconds maximum to complete the runs. The slower we go, the better, so that the robot doesn't shoot past the endpoint. With our gear ratio and motor RPM, we found that we should complete the run within 100 seconds. We calculated that the lead screw would need to be at least 60 millimeters long. And with regards to efficiency, you can see that it's very low, but the aim of the game is cost and accuracy. And to fit with the cost, we have to use a cheap brushed DC motor, which is not very efficient. And for accuracy, we need to use very sticky tyres, so we have a high coefficient of friction, so the robot doesn't shoot past the endpoint. We're using rechargeable batteries, so we don't have a big impact on sustainability. And this is the rating for our motor.
Moving on to the CAD. We started using this quite early on in the design process, straight from the initial sketches. This allowed us to rapidly prototype our ideas, and also in a COVID landscape, it helped us share and collaborate our ideas a lot more effectively. Using CAD allowed us to use computer-aided manufacturing methods, such as laser cutting. Our whole frame is laser cut out of transparent acrylic. This is a very precise and accurate way of manufacturing parts. On the left, you can see the cut sheets which will be sent to the laser cutter. Laser cutting the parts ensures all the bearings run parallel. This would mean that our car would have a higher chance of running straight. And on the left of the screen, you can see an animation of how the frame would be assembled. These are the assembly drawings for our vehicle. On the right, you can see all the parts laid out with dimensions. This would allow someone to cut the parts out of some other material other than acrylic or manufacturing method other than laser cutting. The parts are also annotated and match it with the annotations in the diagram on the left, which shows how the parts would be assembled. Once the vehicle frame had been assembled, additional parts to the design, such as the motors and wheels, need adding. This technical drawing of the exploded view, as well as the animation, show how these parts would be assembled onto the frame. In the CAD package we use called SolidWorks, there's a feature called motion analysis. Unlike a standard animation that links the transformation of parts to each other using ratios, motion analysis calculates the contact between each part. This allows for a more realistic simulation of what the vehicle would do in the real world. As well as being able to see the motion analysis, data can also be drawn, as seen here on the graph. The red line represents the rotational velocity of the motor, while the blue line represents the rotational velocity of the wheel. As you can see, the motor spins faster than the wheel, and this shows the gear reduction we have used in our design to give our vehicle more torque. Finally, you can see an animation of our design in action over a 1 meter course. In the animation, you can see how the mechanical measuring system works in our design. We hope you have enjoyed our presentation, and thank you very much for watching.
Good afternoon, we are the Unthreadables representing UCL, and we will be presenting our unique design for this year's Repeatable Vehicle Challenge. A key aspect of our vehicle is the nut and thread mechanism, which is responsible for mechanically measuring the distance the vehicle travels. As the wheels rotate, so does the thread, but the nut's rotation is restricted by the groove in the base plate. Therefore, it moves away from the button you can see in the images. Once the wall is hit, the motor reverses so the nut moves back in the opposite direction until it reaches the SPDT button, stopping the motor. During real-life testing of the prototype, we discovered an overshooting problem, which we fixed by implementing a 1 mm metal rod attached to the nut, which falls when the nut moves away from the SPDT. And upon the nut's reversal, it pushes the brake button earlier. For the gearbox to have the ratio of 1:64, we had to add a rubber belt to connect the third large green gear to the output shaft, which rotates the wheels. The motor used has a stall torque of 49 GCM and is powered by 3 volts.
In order to arrive at the final design, we went through more than 70 iterations to reach the best possible outcome, while keeping in mind the IMechE rules. Our first design was aimed towards a more heavy and slower car. However, we remain flexible by looking for a drive terrain with multiple speed outputs that can be easily altered. In the development process, we created a real-life prototype which we tested at UCL that helped us verify our calculations and design choices. The processes helped us to uncover the weakness in our design, which improved our understanding of the real-life behavior of the vehicle. Therefore, we were able to implement the necessary adjustments to meet the new objectives of speed and efficiency.
With the new goals of speed and efficiency in mind, our team went on to reduce the vehicle's mass to improve its performance in these areas. To do so, we decreased the chassis width from 17 to 14 millimeters. We removed the sides of the chassis as they were unnecessary. We have the 3D print infill from 10% to 5%. And although we didn't use the generative design outcome, it inspired us to add air pockets in the chassis to reduce the weight. All these changes resulted in a 28% decrease in mass from 513 to 370 grams. Our team also switched from the RE280 to the RE140 motor, which better suits our objectives and can drive our vehicle up a 10-degree incline. Compared to the old motor, for a gearing ratio of 1 to 64, the new motor is 60% faster. Additionally, from the simulation, we observe a 30% decrease in energy consumption.
Here's a summary of the cost of components. The total cost is approximately £25. The two highest costs are the nuts and bolts and the gearbox and motor. To optimize resources yet have room for creativity, we looked at alternative cheap routes for manufacturing basic components using our 3D printers, including the spoiler and the base plate of the vehicle. Moreover, to achieve the most simplistic design, we focused on using a measurement system with the least possible components. Some cost cuts stemmed from the fact that we used hot glue instead of nuts and bolts to fit the components together. We also 3D printed the axle holders and reduced the overall weight by removing unnecessary components, such as the potentiometer. In addition, being comfortably under the £30 cost limit, we decided to buy higher quality batteries from Amazon.
To check the reliability of the simulation, our team compared the output with our own calculated results from an Excel spreadsheet. In both cases, the maximum speed reached by the vehicle, as well as the time taken to complete a 1.5 meter target to wall distance with no angle of inclination, were very similar. This is also the case for the energy calculated, as it was found to be of the same order of magnitude as the simulation output. The IMechE has put a restriction in which no team can have their vehicle exceed a deceleration of 10 G. In our case, the Dpdt button used to reverse the vehicle's motion has a spring attached to it to act as a dampener. With this spring, the maximum deceleration at the wall will approximately be 2.39 G. However, in reality, the button will switch the polarity of the circuit before it reaches that value, and so it is safe to say that the deceleration will never exceed 2.39 G. Thank you for watching our presentation. We hope you enjoyed this animation of our vehicle.
Yeah, well done, everybody. That was great. So what I'm going to do now is I'm going to put the posters for these teams back up so that it acts as a visual cue for the judges to start asking some questions, and so that everyone else who hasn't had the luxury of sort of already seeing these devices, at least they can refresh their memories as to which one we're talking about. So first up is UCLA, and hopefully you'll be able to, can I check, can you see the UCLA poster on the screen?
Yes.
That's good, okay. And judging team, are you there?
Yes. Yes.
Okay, so what we'll do is we'll do the Q&A. We've got up to 10 minutes for each team, and then if you can just keep a note of the Q&A scores, and then we'll put those together during the break. Okay, so I'll hand over to the judges. It's all yours. Judges, are you there?
Yes, if nobody starts, I ask the first question. Hi, it's Davide here. I found quite interesting that you decided to use a cassette tape as a mean to measure the activity. Could you please tell us a bit more about the other option that you investigated? Just try to describe them a bit more in depth. Thank you.
Hello. So I guess we found this solution quite early on,
but we considered as all the teams almost a Screw and Fred, but it was very early on, as I said, that we found this solution, and we thought it was quite unique and something that would stand apart from the others. So yeah, it was quite straightforward for us.
Yeah, the original idea we had was thinking about using thread on 2 spools. And then when we were thinking about it, we realized that a cassette actually did exactly what we wanted to. And we did some testing just to test how strong it was. And we found that it wasn't going to break under the forces we were going to put it under. So we thought that it was a suitable option.
Hello, UCLA. Question from me, if you don't mind. It's Ben Hodgkinson. Firstly, I was very impressed with the design. I like to see a lot of the detail in it. It was another level, so well done on that. I was intrigued. There's some slots on the plastic carrier next to the cassette tape. What are those slots for? Sort of long vertical slots?
They were just to try and add some strength to the bit that holds the cassette tape.
Right. Okay.
Just because previously it looked a little bit flimsy in the cab model. It's not some amazing design.
Right. Okay. And then the switch on the front, I noticed when sort of interrogating the CAD, it looks like it sits on 2 kind of pistons. Can you explain what the function of those is, please?
Yeah, so there's a spring inside each of those pistons, so it's just our shock absorber.
Right.
Just to reduce the impact with the wall, so that if we hit at a slight angle, that the car wouldn't sort of skid and jolt and change its angle.
So were you intending just coil springs or something like that?
Yes, coil springs.
Because I noticed, because when I hid the parts on the model, there was no coil spring present, so I wasn't sure what you'd intended.
Oh, sorry.
Okay, no problem, no problem. And then I started thinking about the exact position of the tape at the start. So when you start the vehicle, is it such that the metal section of the tape is touching both contacts? Is that right? Or will you have one of the contacts on the plastic part of the tape?
I believe we'd have to slightly offset it by a fraction of a millimeter.
Does that mean Does that mean in your design you will definitely overshoot by a couple of millimeters?
It would overshoot by just under the distance that we put that offset on. So the offset could be about a millimeter. So that was within what we thought was an acceptable range.
Can you think of any way around that?
Currently, no.
Okay, interesting. I noticed the chassis plate had sort of black and white layers on the CAD. What was that to represent?
That was just to make it look like the plywood that we intended to cut it out of.
I see. Nice touch. And finally, it's not really a question. I'd just really like to see the detail of how the axle bushes sort of clicked into a plastic retainer and then actually provided some end float control on the wheels. So it's often missed in this competition, end float control. So well done on that. Good effort.
Thank you.
That's all from me.
Okay, hi guys, Tom Cheshire. What do you think the weakest part of this design is? What worries you most about its performance, either breaking down or not achieving the aim? Anyone hear me?
Yeah, I can hear you. I think part of it is possibly the cassette design, because this isn't something we've seen on other designs. So it's a little bit untested, and we haven't had the facilities to put a car together and test it to verify that it would definitely work.
Okay, I love the addition of the tape. It was quite nostalgic. I didn't realise that you guys knew what they even were, to be honest. And you said your FEA analysis resulted in a deflection of about 0.5 millimeter. Did you have any idea of what the limit was? What were you actually looking for, and what would have been an unacceptable result?
We weren't. I mean, we didn't come up with a value that we would have decided that it was unacceptable at. I think it was just a checking, because we had our original design, which was a much like a larger base plane. We just wanted to take it away, and we looked at the results and saw that sort of that seemed intuitively to be a sensible value, but we didn't have a limit. So as to
Okay, thank you.
Sorry, I did have one more question I've just thought of. So I noticed the addition of the laser, and you did explain in your presentation that it was to do with alignment. I guess I've been thinking exactly how does that alignment work? So, because no matter what the angle of the car, you're just going to get a dot on the wall, aren't you? How do you know that makes it aligned?
So the idea before starting the car is to use chalk. So we have a 3-minute period, I guess, to align the car and make adjustments. So the idea was to use, chalk. So one person behind the car, one person on track using chalk to see the line of the laser to the wall, and then just adjust as accurately as possible.
We also thought in the beginning of using a compass to properly align it with the wall, but a good compass would be too expensive and would go over our budget. So that's why we went with the laser method.
Yeah. One other, this is really nitpicking, but the wheels that I know you've sort of used optimization to generate. You haven't ended up with a perfectly rotationally symmetrical design. Why is that? What has the computer got wrong?
When we looked at the wheel in our CAD model afterwards, and the center of mass is in the middle of the wheel, so it's got on one axis, if you flip it, it's the same. But I think it was us working around with the new software of generative design, trying to come up with an interesting design. But it's an area that we could definitely look at as an improvement.
So we simulated different sections of the wheel in generative design, and when we ran the simulation for the whole wheel, you ended up with this obviously very natural design, but the center of mass was no longer in the center of the wheel. So we experimented with making different sections so that we could get that same strength, but with the center of the mass in the middle.
Okay, understood.
Hi, Steve Parkinson, Autodesk. Just actually moving on from Ben's question as well. Using generative on the wheels, what was the performance increase that using that technology for the wheels delivered for you?
I don't think we quantified the wheels specifically. We were trying to save weight across the car as a whole, with the base plate, the wheels, and all of the fastenings. So we haven't quantified the difference made by the wheels individually.
And just an additional question, which is somewhat interrelated, but you referenced the chassis and you optimized the chassis. Did you optimize the chassis using technology, or did you optimize the chassis based on equations, or did you just optimize the chassis based on where you thought it was a good place to remove some material?
So the chassis wasn't optimized using generative design, although we used the FEA tools within Fusion to experiment with removing material and seeing the effects after doing that, until we had a result we were happy with.
Okay, thank you.
Okay, any last questions? I think we're almost up on time.
No, all good from my side.
Okay.
Thank
Sorry,
you very
just
much.
to go
It has
back.
been very good.
Go on, George.
Oh, sorry, just to go back to the final question about the performance gain. So by taking the mass away that we did through JF design, we saved about 15 grams on each of our wheels, which was like more than half of what the wheel was originally. So we managed to make them a lot lighter.
Yeah, and in the simulation, it also appeared to be like savings regarding rotational mass in the wheels. So decreasing the weight of the wheels also help in decreasing the amount of energy consumed.
Okay, thanks very much. Right, so we're going to call a halt there, and we will now move on to, let's go to Durham 1. Go. So Durham 1, are you there? And yeah. Hi guys. Okay, so can you see the poster on the screen, by the way? You
Yes.
can. Yeah. That's good. It must be because I'm presenting. All I can see you guys, but that's great. Okay, posters on the screen. Over to the judges.
Okay, shall I start? Again, I really like this design. I particularly liked all of the square sections that sort of slot into the chassis. I think that will make it very accurate to build and to align all the wheels. So well done on that. One thing I noticed was the wheel bearings were held by 2 plates. Can you explain why it's 2 plates, please?
So one of the plates is solid and one has a hole in it for the bearing to be press fit into. And the plate that's solid allows the bearing to be parallel with the frame. So it's trying to keep things parallel from the laser cutting, basically.
Yeah, I thought that would be your answer. And then you say it's solid, but it has actually got a hole through to clear the axle, right?
Oh yeah.
So which part of a bearing rotates and which part doesn't in your case?
So the inside of the bearing would rotate because that's on the axis, and then the outside of the bearing would stay in place because it's pressure fit.
Yeah. So now I've asked you that leading question. The through hole in the what you called the solid plate looked like it was only just big enough to clear the axle.
Yeah.
And so it would actually touch the inner race, which would be rotating. Do you see my point?
Yes.
Okay, so it's a real minor point. I really like the detail. It's excellent that you've put 2 plates in there to try and to square it up, but you really only need to square it up on the outer race. So just there's a bit of free friction there for you, a few milliseconds I found for you. So that's good. And then one thing that I was a little concerned about was I couldn't see any way that end float was controlled on the axle and wheels. So could they slide from side to side? How was that controlled?
Yes, we don't have any kind of end flow control, but the tolerance between where the bearing is and where the wheel mounts is quite tight. So yes, it could slide, but it's not going to make too much of a difference.
Having seen, I've had the advantage of seeing a few of these competitions in real life, or IRL as you kids would say nowadays. But the keeping the wheels controlled and in a straight line is exactly what you need to do to be able to bring the vehicle back to its target, because otherwise you'll find it will track. The wheels will sort of track one way as it goes up the track, and they'll track the other way coming down the track, and it'll lead to quite a bit of side-to-side misalignment. So keeping the wheels straight and true is critical to the accuracy of these vehicles. I've noticed on the on your Dpdt switch, you've got no spring mechanism at all. Do you know whether the switch is going to be okay with the impact against the wall?
That would probably be one of my primary concerns for the design.
but we're using a big 12-volt motor. So my hope would be that that would be strong enough to change the direction of the car quick enough to not damage the Dpdt switch.
So have you got anything other than hope and worry, or have you done any engineering on it?
Well, I don't know. It would be a thing that would have to be tested, and obviously we haven't got to fully test it in real life. But
so sorry,
that could be an improvement that could be made.
Well, I'm being a bit tough on you, really, but what I'm trying to get at is that don't wait for testing either. I don't wait for testing when I'm designing bits for racing cars. You have to do some calculations to check that if you're worried about something, then do some calculations to verify whether it's okay or not. That's kind of the advice I'm trying to give. I was trying to work out how you actually started the vehicle. Is there an on-off switch at all?
Yeah. So I don't think you can see the circuit diagram too well, but we've got two on-off switches. One is the push switch, which the nut on the lead screw turns off, and the other one is a rocker on-off switch. So
okay.
that's what we'll use to start it at the beginning.
Great. So like I said, I really like the vehicle, particularly like the way it assembles and the fact that you've got wheel bearings. So well done on that. I think that's the last question from me.
Okay, shall I go next?
Thanks,
guys. Great design. One thing that I was really interested in, you got a factor of safety of 6 on that Axial, I think it is. And when I see a factor of safety that big, I think it's probably over-engineered. Could you have saved something by going a bit closer to the limit, if you like?
Here you go.
What do you mean by over-engineered? Do you mean we could have used? Oh yeah, we could have used thinner axles, I guess, to save cost.
Yep. What sort of stuff? That sort of margin doesn't come for free when you're designing stuff. And usually, if you've got that much of a factor of safety, there's something you can save and use what you save elsewhere to improve the design.
Yeah, I think one of the problems associated with that is with the wheels. So using a much thinner axle might have been more of a problem in connecting it in the assembly. But it's certainly an improvement we could have looked to make.
Okay. And I liked your the weighted matrix you did at the start. That's a tried and tested method of doing this sort of thing. How did you decide on your weightings?
Well, basically anything, or sort of accuracy of it and reliability was always very high, because it needs to be able to hit the target and hit it consistently over several runs. Anything that sort of could be assessed but isn't necessarily the main aim, so sort of robustness, durability, that would be secondary, and also cost, I suppose. And then the bottom things are aesthetics and, I suppose, assembly. So anything that was being judged as high, anything that you could look at and scrutinize, sort of middle, and anything not really relevant, low.
Okay, thanks. And like Ben, I was quite interested in your bearing designs. You know, using those ball bearings is presumably quite costly and quite heavy. What other options did you consider?
I don't know. We wanted to use ball bearings to try and keep all the axles parallel and also reduce friction. It did add some additional weight, but we thought that compromise was necessary.
Okay, but did you have any? What were the other options that you had in mind, if any?
Honestly, we kind of had ball bearings kind of right from the start. We could have used some kind of maybe 3D printed mount to it could have been friction based with some like graphene to reduce friction, but yeah, we had ball bearings in mind from quite early on.
Okay, thanks. That's me done.
Morning, everybody. David here. First of all, my congratulations, because your design and your presentation was very, very nice. I personally liked a lot your idea to minimize the scrap by fitting on one single thickness of one commercial material, everything on a commercial size, so that you can physically buy this plastic material and get it laser cut through any place in the world. So well done. It's a very, very good design for manufacturing approach that you have done. A couple of questions from my side. You declared that you chosen these sticky wheels to improve the friction and get better control on traction and get other stuff. Are these commercial items? Did you select different items? How did you find them?
Yes, the wheels are commercial. They're quite standard electronic, like hobbyist wheels. So they're available all over basically. So we could easily source them and buy them.
Did you analyze different sources, different products, or you just went for the cheapest one because there was a budget constraint?
There are several sources. We just went for what was the cheapest supplier. Because with our engine, we had to get the part within 4 weeks, because that was the slowest part. So the cheapest part that also came in that time frame, that's what we went with.
Yes, great, fantastic. Now, looking at your design, on top of the concerns that have been raised by my very estimated colleagues over here, I was thinking about the balancing, the weight position overall of the vehicle. So if you don't control the position of the axle, so you rely only on the friction of the assembly of the bearing in the side, it could be risky, but it could be fine for this purpose of the vehicle. Something that may not really help you is the position of the battery pack. So if you have a weight which is unbalanced, the small deflection and the small deflection of the tire may make your car steer differently. So you have two things here: the precision of alignment of your system that is not controlled by proper shoulders in the axles, and the uneven positioning of the batteries, which are an heavy component both in real life cars as well as in your prototype. Did you analyze these differently?
In terms of the batteries and the balance, if we had more of an aerial shot, we might be able to see better. But there's quite a big area in which we could put the batteries. So in testing, we could find out, is the car turning to the right, at which point we can move the batteries quite a lot closer to the motor to improve balance.
Thank you for your answer. Again, I just go back to the comment that Ben made before. I would recommend you in the future as an approach to do as much as possible from the design and leave the testing, if it's possible in the ideal world, just to validate that your design was correct. It could be tempting to use the test as alignment for your design, but it may lead you to more loop, more errors, and overall a bigger time. So anyway, again, my very deep compliments for you. You did a very good job, and thank you very much again. I'm done at this point. Thank you.
Okay, I'm just keeping an eye on the time. Stephen, have you got a question? And then we need to move on.
A quick question from me. It was good to see the use of some motion analysis. My question to you is, how did you use the data captured from motion analysis to feed it back into improving and developing your overall solution?
I'll be honest, like the motion analysis, it was more kind of like proof of concept to things that you you could measure to improve the design, but we didn't use it to like alter the design in any way, to be honest.
Okay, and on that note, then, did you use any of your CAD information to feed back in at any point?
There were certain moments in the CAD design where, from designing it in CAD, you realised that something would not work, like something like there'd be a collision somehow that if you were like drawing it, like sketching it, you might not have realised, but then in CAD, you can like realise that a lot better. We did initially, we were using a lot smaller teeth on the gears, but then we realized that we should increase the size of the teeth in the gears because we thought like that basically a laser cutter wouldn't be accurate enough to cut fine teeth, so we increased the size.
Okay, thank you, Andrew. Thank you, team.
Excellent, well done, guys. That was very good. So you can relax now for a moment, and we'll move on to UCL B. So I'll just find your slide, your poster, and UCL B. Are you there? Okay.
Yes,
Yes.
2 seconds. Let's. Oh. Just got a crash of that. Okay, can you see the poster?
No, I think you're on share your screen.
Yeah, it just crashed. So 2 seconds, and we'll get that back. There we go. Judges, are you ready?
Yes.
All yours. Go for it.
Hello there. Again, I really like this design. It was I particularly like the fact that that you've built a prototype, and I saw the little pictures of that, and I even had a go at using your magic square to have a look at the video there as well. So it's a nice touch. I did have a question that you actually answered in your presentation, which was, what is that intriguing little pin on the lead screw nut? So just tell me about a bit more detail about that anyway. I think I now understand it, but please just explain it anyway.
I would love to explain that to you. It's a very good observation. It kind of relates to that question you asked for the first team about the cassette tape and the overshooting problem, because the way we're designing this nut and bolt mechanism, we are depending on a button which being pushed after the nut moves a certain distance forward and backward. But in the beginning, the nut cannot be pushing the button because the electricity wouldn't be flowing in the circuit and the car wouldn't be moving.
Yeah.
So we have to offset the nut slightly forward, okay, so that the circuit will be closed and the car can move when we push the on button, okay. But as you mentioned before, when the car reverses back, this overshooting, this offsetting of the nut is going to make the car overshoot. And from real life tests, we noticed that it wasn't like 1-2 millimeter. It put us on the third part of the bullseye, which was very bad. So what we ended up doing, after lots of thinking, we came up with this 1 millimeter rod, which I used like a keychain, you know, like this part in the keychain, which is you put the keys in, obviously. So we got that and we made it straight, and I reprinted the nut again, and we made this nut, this metal pin falls down due to gravity after it moves back. Okay, so when it reverses back to the button again, it pushes the SPDT button early and make the car offshoot perfectly in position. You might ask, how did we do that? How did we know it's going to offset perfectly? That was basically trial and error, finding the perfect thickness of this metal rod. I started with 2 millimeter, 1 millimeter, couldn't go any less than 1 millimeter. But we found out that 1 millimeter was the perfect thickness for this metal rod to make it overshoot perfectly.
Okay. Can you think of a an electronic solution to that?
Electronic solution, because our approach was purely mechanical. I cannot think of any solution for that, because whatever mechanical mechanism, as all of the teams, they all have overshooting problem, which might not be addressed, whether it's a cassette tape or other nuts and sled, we're gonna have overshooting problem. And I don't think any electronic part might fix that, because you're always gonna have a physical part which need not to be touching this button in the beginning.
What about a push button switch in parallel with the one that's activated by the lead screw, which you'll use as your go button? What about that?
A push button in parallel to the SPDT? Was it going to be mounted?
Just on the chassis somewhere, and you just press that button to start it.
Okay, you mean?
You understand what I mean?
So at the beginning of the competition, we pushed.
So yeah, you're.
Sorry.
Go on. You first.
Yeah, I was just gonna say we already have the push button implemented. That's how we're gonna start the vehicle, and then there's the SPDT switch, which is gonna stop the vehicle from moving, and then the Dpdt, which is what reverses the vehicle. So there's 3 different switches.
I think I know what Ben means. Ben means that we should be putting our finger for like a second extra, so we can give the car a push ahead. But I'm not sure if that would be allowed in the rules, because you just have to touch the car once and let it go. But from your idea, from what I understand, you want a push button where we can close the circuit until this offsetting happens, and then the car can move and come back. But I'm not sure if I keep putting my finger on the car while it's moving.
It depends how long you have to press it for, I suppose, doesn't it?
Well, yeah, depends on the offset, exactly. Yeah, we can make that by having a longer sled, but that's a good idea.
Something I couldn't quite work out in the chassis structure was it appeared to there's a bottom plate that you could take off, and then there appeared to be 3 tubes on the inside. What was all that about?
Oh, so initially we had the goal of the competition was accuracy. So we thought of actually making those as sand holes. So we would insert sand to make it heavier so that it could go slower. But then to increase the mass, obviously. But then the objective changed, and we actually saw that this was it was working to our advantage also, because we could just simply remove the sand and reduce the mass, and therefore make it go faster.
Okay, understood. And I also noticed that you had some nice end float control on the wheels, so I did enjoy seeing that. So overall, a very good design. So thank you. I think that's the last question from me.
Thank you, Ben.
Hello.
Hello.
Hi. Anyway, thank you very much again for all your design. It has been very, very nice to look at it. Well, very, very, very well done. With all the constraints over here. I really like the idea of making your own non-hexagonal custom effectively nut to be guided into a slot. So, first question is, did you analyze if the friction into that guide, so between the screw system and the additional friction for that nut, was going to affect your performance anyhow?
Ibrahim, would you like to answer this? Or shall I go?
Hi, yeah, so we when we 3D printed the parts, we like the nut and thread, we noticed that it's a very good 3D print, so it was very smooth. We didn't have any problems, and additionally, to stop it from having friction against the walls of the chassis and inside the thread, we thought of spraying it with WD-40 lubrication to make it much smoother and to reduce the friction in the parts, in all the moving parts during the competition.
Okay, effectively lubricating different materials within a joint is always a nice thought. Just a suggestion from my side, be conscious of the chemical compatibility. So some lubricants could contain some solvent or some other parts that could affect your plastics. So good thought, well done, but again, it's something that by design you could think about. Well done again. Something that I noticed, I really like the fact that you made effectively the front track and the rear track different, put a little bit of design, making it looking like a car. So you have put some time and some effort, not only to do your competition on time, but as well to make the car look like a real car. So again, well done. Given that the car is going forward and backward, I need to go back at the same point. Have you thought that having a track which is different in width from the front and rear, so from reversing and going back, could affect your straightness or your effective straight direction?
So are you talking about the airfoil, that the airfoil is in the back? What's going to happen when the car is reversing?
No, I'm talking about the width. So the front track and the rear track are different. So the car may behave differently in a straight line while going forward and coming backward.
Okay, yeah, I see what you mean. So basically, we got inspired with the design from online because we, after doing some research, realized that making the driving axle wheels having shorter distance between them than the one in the front made the car more stable. But obviously, as you said, what about what happened when it reverses? So this question was answered from real life testing. We saw that because the car is not moving with like super high speeds, we saw that it doesn't really make any difference in real life for this design. But if you're talking about a real car with like 2 tons weight, might be a different case.
Okay, good, thank you. I think that given that anyway, the front axle and the rear axle are different because on one you have the gear and on the other one you have the screw. You didn't have any commonality problem with having the same, absolutely exactly the same axle that could bring your BOM cost down. But anyway, well done. Last from my side, your car is nice, has a good footprint. Have you thought that having a single point for the Dpdt switch instead of having like a square bumper was potentially inducing a skew effect when it contacted the wall, or did you thought that that was not really an issue?
Zarina, would you like to ask
Yeah,
that?
so initially when we were working on the design and developing it, we did include a small plastic bumper at the front where the switch is. However, then when we built the actual car in real life, we saw that there wasn't much that the additional bumper was adding because the switch in itself has a spring. And because, initially the car doesn't hit the wall at such a high speed for it to start flying off at a tangent, we gathered the information from testing that this was sufficient and this was, helping us to achieve the objectives that we have.
And just to add to that, we tried as well overclocking the engine by adding a 9-volt battery so the car can go as fast as possible. And we tested the Dpdt button without the bumper, and still it was sufficient to dampen the car without any deflection.
Okay, this activity that you have done is very, very good, very value added. Is a very good practice to put something in and by test decide if your design could become simpler. Again, well done, and I'm really impressed by such achievement by all the teams, all the young teams that are here. I'm done for the moment. Thank you.
Thank you, David. Very kind words. Thank you.
Morning, guys. Tom Cheshire here. Can you just remind me why you ended up using a rubber band in the gearbox?
Yeah. Marwan, you can go ahead.
Okay. So can I share my screen? Would that be possible, Tim? Or that would ruin your presentation?
No, we're not sharing screens on this section. Yeah.
Okay, no problem. That's fine. I can draw a mental image for you. So basically, we have our gear terrain. It's quite compact, okay? And we have the small gears have 12 teeth, and the big ones have 48 teeth. Okay, so the first mesh is going to give you 12 to 48, which is around 1 to 6, or maybe a bit different. Don't remember exactly.
1 to 4.
And then 1 to 4, and then you're going to mesh it with another gear. So it's going to give you 1 to 16, and then you're going to mesh it with the third gear. It's going to give you 1 to 64 overall gear reduction. But the problem that this 1:64 gear, which is the third one, was a bit offsetted from our axle. Okay, and because we already designed the car, so we couldn't push the gearbox any different. So this gear would be mounted to the axles. So we just ended up adding a simple rubber band, which is commercially available, so it can drive the axle and drive the car.
Okay, thanks. So what problems do you think the rubber band might have introduced? It's not as efficient, obviously, as using gears. What? How did you change the design as a result of having to use that rubber band?
So we didn't do that in real life, but I would expect in real life there might be some skipping. So what I would approach is would make the two pulleys have some teeth on them, and I would buy a rubber band with some teeth on it as well. So skipping wouldn't be possible, and it would be almost as efficient as a gear.
And what about bearings? Because obviously the rubber band's got some tension on it, and is going to introduce some moment into the into the bearing assembly in the gearbox.
There is no bearings in the gearbox. They're all plastic mounted on a piece of aluminum.
That's my point entirely. So the rubber band is going to be in tension, and you're going to introduce more friction into the joint between the rotating bars and the mounts. I wonder if you had thought about that.
Yeah, of course. Like you mean, like the rubber band might be too tight. It's gonna push the gear to the axle. It's gonna make it kind of breaks. That might happen, but I don't think any rubber band is gonna be that tight, because if it's that tight, it's not gonna rotate anyway. And even if it is, we're talking about a very miniature scale of a car. So stuff like that wouldn't really affect the car moving that much, from my perspective. I didn't test it in real life yet.
Okay, thanks. I think we're quite short of time, so that's me. Thanks.
Hi, yeah, Steve Parkinson. Just a quick question. You mentioned you achieved weight reduction by doing some calculations and using some of the generative topology optimization in the software as an inspiration. So you never used that as the final outcome. How did you transfer what you found from what the computer told you into what you then created from that?
Ibrahim would be good to answer this. Ibrahim?
Yeah, so when we used the generative design on the chassis, it gave us some design which wasn't the one that we wanted, and we didn't really want to use the one that it gave us. So instead, what we did is we took inspiration from that. The inspiration that we took is from the generative design. It introduced some hollow parts inside of the chassis. So we thought of maybe adding more hollow parts in the chassis of the car would be a good idea to reduce the weight while keeping the structural integrity the same. And so we did that.
And did you compare the data from before using generative to after, when you created your new component part shape, to see if there was any difference and significant advantage to doing that?
Yeah, there was massive difference. The initial weight of the PLA printed base was 540 grams. And after we got inspired by hollowing the chassis and having this kind of 2U shape cut in the chassis, the car chassis is now 260 grams. So it's almost half.
Okay, thank you.
Well done, guys. Thank you very much. Just keeping an eye on the time. So thanks, well done, all of you, all of the teams for coping with that. I'm sure that some of you that weren't in the top 3 are now breathing a sigh of relief, having witnessed that. And I can confirm that Ben's actually working for Red Bull, not Pitbull, based on the questioning we've just witnessed. However, those of you that are sort of sitting comfortably and thinking you've got away with it, Ben, are you there? Do you want to? We have got time before the virtual final. If you'd like to just do a quick screen share, and we can look at some of the other designs. If you wanted to just pass some comments. So, what do you think?
Yeah, I'm happy to do that.
Okay, that's something we discussed. So, Brunel, are you there?
Yes, we are here.
Good, good. Okay. Just to remind Ben, this is just to pass your comments on what you found on the design. So there's no scoring as such involved with this, but I think it's nice to be able to share all of your incredible efforts, and you know, we don't want just sitting there and we didn't get to see your presentations. So I'm going to share screen. I've got the CAD on my screen, and then I will manipulate, and Ben will discuss and no doubt highlight things that he'd like us to be able to see. So hopefully you can see.
Oh yeah, this one.
There we go.
It was definitely an intriguing design. This one, I like the structure. I am intrigued why you made the decision to go for the angled wheels.
It's to keep the direction.
To minimize our deflection when the vehicle goes forward. So because we have no means to change direction on the front wheels, we putting this 15 angle camber on the back wheels will minimize the deflection of the vehicle.
Right, so it's an attempt to make sure it doesn't steer.
Yes.
It just runs true. Okay. I think the reality of actually achieving that, you might find that it's made it a touch more difficult for you, really. There's something about an axle that goes straight through the chassis that kind of helps keeping it all square. But if you could genuinely get two perfect 15-degree angles and they were normal to the chassis, you stand a chance at it going in a straight line. But just manufacturing tolerances might mean that what you're trying to achieve there is a bit ambitious. I noticed I think there might be a bit of an end float issue on many of the wheels and shafts and gears. Is that something you thought of?
I'm sorry, could you repeat the question?
I'm worried about the axial alignment of the gears. There's nothing that seems to stop the shaft floating from left to right. And especially when you look at I noticed you've used a bevel gear on the drive.
Yes.
If you could pan right a little bit for me, Tim, thanks. So a bevel gear, one of its side effects is it'll try to push that shaft towards the screen top.
Okay, because we are using steel rods as axles, I think if we just pinched the axles with the pliers, like on the old toy cars, we resolve the issue of deflection.
It doesn't. Won't that stop it rotating?
No, you just add some pinches left and right to the place where the axle goes through the chassis.
Okay. I think you might find in reality that's quite difficult to achieve with the sort of precision that you'd need. I think I've seen other teams and I've seen other toy cars just use a simple tube over the top of the axle to control the end float. So just a top tip that you should really try and look at end float control on that, especially with bevel gears, because it will drive that wheel set to one side. Okay. The bevel gears, did you model those yourself, or was that a grab CAD?
No, the bevel gears were modeled from scratch, and the normal gears were modeled using a fusion add-on, which is called Helical Gears Plus.
Okay, that's very impressive to model the gears, the bevel gears like that. So well done on that, and the detail on the model with the breadboard and even the wire runs is very impressive. One question I have got is, do you know the term coil bound? Do you know what I mean by coil bound?
Yes.
Okay, so if you look at the spring on the vehicle, I haven't done the measure, but just if you look at the thickness of the wire that you've used on that spring and the number of coils, I think the coil bound height of that spring is taller than the switch.
I agree. We have thought about that, and we know that we have after testing, we should have a perfect place to set the switch right at the point where the vehicle stops or the spring stops tensioning.
So how are you going to adjust the position of the switch?
Well, because all the chassis is 3D printed, we can add a support for the switch in front.
Okay, and then those 4 rods on that on that bumper, are they a sliding fit in the rear of the chassis or front of the chassis?
Yeah, they're supposed to slide inwards, so the front bumper always stays in an upright position, and it was thought that way, so we also minimize lateral deflection once we hit the wall.
Yeah, I think that's good. It's a detail, but as I say to my engineers all the time, the devil is in the detail. What stops those rods from falling out of the rail?
Nothing in this model.
Yeah, and the spring presumably is under a little bit of compression at that point as well, so the spring will literally just push it out, and the bumper will be on the floor. So you just need maybe little circlips on the end there, or maybe just a flange on the end of the shaft or something like that. Is all it needs. Okay.
That's good. Ben, can I hurry you along? I know you're enjoying this, but we need to.
Of
We've added
course.
this in as an extra because the virtual competition doesn't take too long. So if anyone has joined recently and didn't see the agenda at the beginning, so yeah, well done, Brunel. I'm gonna move on next to I think it's Durham 2. So Durham 2, are you ready? I'm just going to open your model file.
So while it's opening, there's bevel gears used in this vehicle as well, aren't there? Can you zoom in on those for me, please, Tim?
Yeah.
Yeah. So what controls the end float of your front axle? Same question really as the other team.
Yeah, to be fair, we probably could have done a bit more to control it, but we do have quite tight tolerances with the axle. To be fair, the CAD it doesn't really look too great, but there is quite tight tolerances. But I think on reflection, we probably would have considered a bit more on a redesign.
Yeah, have you got is it an actual bearing or is it just a bush?
It's a plastic bearing, yeah.
Yeah, so it's just a bush. So therefore, it needs to be clearance for the axle to rotate, right?
Yeah.
So it can't control the infloat. You need a separate piece to control the infloat, or a change in diameter of the shaft or something, or tube slipped over. But it's the same point as the last team, so I won't labour it. The lead screw mechanism I thought was a bit interesting. Is the hex on the end of it? Is that supposed to be the bit that follows? And
James, if you.
It's a stopper, so it's attached to the lead screw. So it as the lead screw passes in and out, so it doesn't stay move from the end. It stays on the end.
Right. So what stops the lead screw from just rotating rather than, because you want a lead screw to, I think if I understand the design correctly, there's a female thread inside that gear, right? Is there?
Yes.
And
well,
so
inside the connector, which
inside the the bit bolted to the gear, and so you want the lead screw to not rotate, and the connector piece to rotate so that it draws the lead screw through it, right?
Yeah.
So what stops the lead screw from rotating?
Because the connector is attached to the gear and it's connected to the motor, it should only allow the lead screw to move in and out. Because if one of the two would have to rotate, and if the connector started rotating, then something would go wrong with the axle at that point.
I think because of just the friction between the thread and the screw, I think what will happen with that is the lead screw and the connector will just all rotate together, and the lead screw won't actually move. That's what I think will probably happen. You see what I'm getting at? Yeah. Okay. And then there was just
we did do some calculations on it, and it's in our presentation, and I thought it was not significant enough for it to attach, but maybe the calculations were off.
Just think you need a physical mechanism to stop the lead screw from rotating. I think that's what you need. Some people have another rod that's parallel to the whole thing that runs through some holes or something like that. Okay. And then one last, I noticed a clash between the gear and the fastener. If you just rotate a little bit right down the bottom there. See that? I don't know if you noticed that, but that.
Oh, I think that's in that is because the actual little the bolt would actually be tightened. I didn't tighten the CAD, so it would be more in. So there would be a.
Well, I agree, but once the nut's tightened all the way down, the thread's too long. It's probably just short. You'd have found it out if you actually made it physically, but you'd have just done shorter bolts and it'd be fine. But
yeah,
we normally don't let the physical world teach us those things when the CAD can point out the clashes for you. So that's all. Okay. That's all. Is that long enough, Tim?
Excellent. Well done, guys. You survived.
Yeah.
That's good. Yeah. Excellent.
Yeah,
right.
sorry.
Next, we're going to move on to, I believe we're on to Kingston Team One. So, guys, are you there?
Hi. Yes.
Here we go.
Right. First question I've got is the spur gear, the one that's the smaller diameter gear that's on the axle.
Yes.
Doesn't look like it properly meshes with the main gear. What's going on with that?
It's supposed to. When we try to design it, we try to design so that the teeth fits perfectly in.
It's only got sort of 5 teeth on it, though, hasn't it?
Yeah, but it should. After what the design that we did, it seems to do what we decided to do.
Okay.
Yeah.
If it doesn't, that's a mistake on my part. I was the one designing the thing. It doesn't. Yeah, I can think I got the actual size of like the actual like gear knobs right, but then spacing I've messed up, haven't I?
Yeah. Okay. Okay, no problem. And I actually wasn't sure. I stared at this for a little while, and I wasn't quite sure how the distance measure worked. So I don't know if you could explain it to me.
I can do that one. You see, the larger gear, there's got one extended tooth. So while the vehicle is traveling, that tooth is rotating forward, and then when the vehicle is moving backwards, it's going to obviously rotate the other way. So the elongated tooth activates that button as like a kill switch. But it also will then stop from moving any further because the gear cannot move any further as well. So it would stop it dead on where it started off from.
Right. Okay. My only other comment that I feel with the size of that gear, the ratio that you've got is massive. This thing will go very, very fast.
We limited the speed of the motor with a pulse width module, if I'm saying that correctly. Just
modulator,
yeah.
So that's okay. So that's what that little electronics is all about as well.
Yes.
Right. Okay. I think have you done the calcs to check that it's got enough torque to be able to drive it?
Yes, we have. We deliberately got a motor that was a quite high torque, so we could, because that was our original design. We found out didn't move because we did the calculations wrong, basically. So then we had to replace the motor, but this one has got more than enough.
That's it. Okay. We've not tested it, so I can't be sure, but I would be concerned that because of the mechanical disadvantage that you've got because you've decided to do a large drive gear and a small spur. I'd be worried that
that was a mistake on our part because we were supposed to have an Arduino in this, but we later found out that we weren't allowed to use an Arduino, and then we had to kind of quickly rethink our concept. And the optimal would be, of course, having the small gear on the motor and a large gear on the axle, but that would require like a large redesign. So we just didn't have the time. So we went with this, and we were assured by one of the technicians that this would not be an issue.
I'm not convinced, but we'll have to just hopefully you can get to build something like it one day and see.
Yeah, hopefully.
Yeah. Okay, that's all I've got on that one, I think. Thank you.
Good. Well done, Kingston 1. Thank you very much. Okay, next one. Kingston 2, are you ready?
Yes, hello, good morning.
Hello, good morning.
Okay.
This is the one with the one wheel with spokes. Explain to me about
correct, yes.
about your spoked wheel. I couldn't quite understand that. Do you want to flip it around for me, Tim?
Sure, no problem.
What's that all about?
So essentially, there are the axle is going to protrude into the wheel. So you would need a spoke there in order for it to stop it. If you were just relying on it to press into the wheel for friction, you would probably destroy the wheel. So that is set so that you would set it when it was setting off, and ideally it would return right into that spoke. Obviously, for accuracy, you could add more spokes, but we found that that was relative to start off.
Okay, so that's how your distance measure works, is it?
Yes.
Right. So would you mind explaining to me a bit more detail about how the distance measure works? Because it's something I couldn't quite figure out, I'm afraid.
Sure, no problem. So there's a DC motor which is going to drive a belt that you see in front of you, and there is a small cog assembly which is going to wind a threaded shaft which is inside, and that threaded shaft is going to spin so it's going to spin one revolution of the threaded shaft per revolution of the wheel. And then when it's driving in the opposite direction, it'll thread in the opposite way, protruding into the spokes, so stopping the vehicle.
So does that toothed belt sit on the threads of the shaft?
No, it sits on a separate assembly. So there's multiple assemblies there. It's not sitting on the threaded shaft. There's another piece inside, which is actually the winding section.
So I think you've got the same problem as the other team. How do you stop the lead screw from rotating?
So that's why the other section is inside there. So that will kind of direct the screw, which is why the other section's there. And then once that's why there had to be two sections, because otherwise the shaft would just continue to spin and it would go nowhere. So because there's that second section, it allows the shaft to kind of take into that section rather than just spinning forever. If that makes sense.
I haven't 100% got it, but I think I know what you're trying to achieve. Okay. Then the end float on the wheels, I think, is missing. Similar theme to what I've said to the other teams. So, do you agree, or have I missed something?
What are you referring to? Sorry.
So I think the wheels the whole axle assembly will traverse either left or right until the wheels rubbing against the chassis, I think.
Could do. That wasn't necessarily something we thought about because of the speed that it was necessarily traversing at, and also the distance. It might be small, like kind of a creep version, but we don't think it'll be a major issue as far as sliding in or out.
Okay. I've seen enough of these competitions to know it is an issue.
Okay.
if you need to control the inflow of the wheels for sure, and all the gears. Okay. And then one minor point, if you excuse the pun, I think you're missing the point. There is no pointer on it, I don't think, is there, on this vehicle? I couldn't see it anyway. You know, the pointer that's supposed to point at the target.
Oh, that would be the spring side.
Okay, you just haven't modelled it. Is that right?
I mean, are you talking about the point that would be on the target itself? There's supposed
to be a little hook that points at the target, isn't there?
Oh yes, of course. Sorry, that would be on this side here that you're currently looking at. We didn't model it or put it in.
Okay.
Unfortunately, if we had known, we would have done, but we just didn't really think of that.
Okay, fine. All right. Nice. I like it's fairly aggressive distance measuring with putting a stick through your spokes.
It's very
but I've not seen that before, so I like the innovation.
Yeah, but it was kind of proof of concept as well. I was kind of curious myself, so I just kind of ran with it and decided to see where it would go, and it turned out a lot better than I thought it would. And it was a good process. I enjoyed it a lot.
Cool, thank you. I'm done, Tim.
Great. Well done, guys.
Thank you very much.
Okay. Next. Okay, on to Hertfordshire. Are you there?
Yep. Hello.
Hi guys, your model's just loading, and then it's over to Ben.
Well, I noticed on this one, as I've criticised all the other teams about end float control, I think you have some very nice end float control on this one. So if you can zoom in on that, Tim, I think if I've seen it correctly, particularly next to the bevel gear, if you've got that, there's a the way that the bevel gear sort of sits on the axle support means that it'll push against there, because bevel gears always create that thrust, so that's nicely controlled. And then if I'm understanding the model correctly, those grey bits on the outside are sleeves over the axle, is that right?
Yeah, they're spacers with slightly larger diameter, so they don't pinch the axle.
Perfect. So nice detail on there. So well done for doing that. The lead screw has intrigued me. It looks way too short for a 4 meter track and the sort of gear ratio that you've got. Have you worked out how far the nut on the lead screw is going to move for 4 meters?
I don't have the presentation up at the moment, but we calculated with the bevel gear, it's a 1 to 2. So for every 2 rotations of the wheel, you get 1 rotation of the lead screw, I believe it was. I would need to double check that. But then
so I can count the number of pitches on that. It's only about 15 or something.
The pitch of we only had 2 weeks, unfortunately, from the start to the end. So the pitch isn't relevant to the one we actually used. This is a 2 millimeter pitch, and we used a 1.5, I believe it was.
Gosh, but not very different. So you're only going to be 20 revolutions of your lead screw before you've touched the switch, right?
And I need to double check, but I think what I calculated it to be was 18 millimeters, and I think we have 28 millimeters of travel.
I'm pretty sure you've got something wrong there, guys.
It is possible. I do have the prototype. I never used a full 4 meter track, but it never stopped prematurely.
Perhaps that's because you didn't use the full 4 meter track.
It's possible.
I just almost don't need to do the maths. I could just see the diameter of the wheel when you work out what the rolling distance is of that, and how many rotations of that wheel to get 4 meters would be way more than the number of pitches that you've got in that gap, I think, unfortunately. Okay, I won't keep labouring the point. I really like the fact that you modelled all the wires and the detail and the breadboard. That's a nice touch. I thought the level of detail in this model was excellent. So well done on that. It's very important to get that in your models. And I like the grub screws that are holding all the end float control in the gearbox. So that's a little collar, isn't there, to control the end float. So
yeah, otherwise it was coming out of slots quite a lot.
Did you think of that yourself, or is it because you've made one and seen it?
We did it originally anyway, but it also allowed us to refine it quite well, because sometimes it'll be too tight, sometimes it'll be too loose. So using those collars, we could actually move it and have some space so that they didn't crash into each other.
Yeah, nice. Very good. I like it. So a good effort. I think you've got your sums on your lead screw length a bit wrong. The principle's great, but the lead screw needs to be more like the length of the vehicle, I think.
Thank you.
Okay.
Excellent. Well done, Hertfordshire.
Yeah. Well done, everybody.
That's good. Great. It's okay. So Ben's going to stand down now, so you can all relax now. It's okay. You take it easy. So what we're going to do now is I'll stop screen sharing. I'm going to move back to another presentation, and we are going to go to the virtual competition. Okay, so that's going to be the next. So again, just one of my awkward pauses while I get things sorted out my end. Okay, here we go. That one and that. Okay, this should be where we left off at the presentation competition. Someone just give me a yay that you can see the slides okay?
Yes. Yes.
Yep.
Okay, good. So this is where it's going to get interesting. So what we're going to do is we're going to show you the leaderboard heading into the virtual competition. So this is the state of play before the virtual competition. So this is adding up what we've got so far with the posters, the presentations, and the design. All right, so this is the current leaderboard. Now, just to mention, I know that we probably didn't mention enough at the beginning that we've invited Durham along to join our regional final because we're the only region that's actually running a virtual competition. I should really have perhaps made more of a point at the beginning to say welcome to Durham. It's been fascinating to watch your designs and so on as part of the competition. Thanks very much for joining us. It's been very, very welcome. And I can imagine that it does get quite competitive from this point onwards. So let me just say, don't worry, Durham can't run away with the Greater London Region trophy. All right, so don't panic about that. It's just that we wanted to encourage participation and invited them along. So Greater London teams, don't panic. This is the overall leaderboard, but as we progress through now with the virtual competition and then to the final leaderboard and the winners, then we will we'll still have an overall leaderboard, but then we will separate it out into the Northeast region and the Greater London region. But as it stands right now, this is the leaderboard. This is just the order. Behind the scenes, the scores are incredibly close. I can tell you that. So it definitely all rests on what happens next. So if you're looking at your team and feeling that you're further down the leaderboard, don't panic. And if you're feeling like you're feeling pleased with yourselves because you're near the top, then just watch out. Okay, so that's the leaderboard as we go into this next stage. So now what's going to happen? You've had the beta app that you've been developing. We've now got the completely unlocked version. So this is where we are going to have different ranges, different elevations. So either the board is tipping up and tipping down. And again, for us behind the scenes, it's been quite interesting because we wanted to create, rather than just a series of individual runs, which would get a bit tedious, what we've done is we've put all of them together so that they all run on a single lane all at the same time. While I say that, Ishmael, are you on the call? Because I know that you have a few things you've had to drop in and out of. Are you actually with us at the moment?
Hi Jim. Yep.
Yes. So just to say to Ishmael, I can tell which call you're on in the background by the other voice. So yep, just to say, Ishmael has been the driving force behind the virtual app. I sort of had the idea and spoke to Ishmael, and we decided it's something we could do. So it's been his genius that has put this together for us. So just to say, Ishmael, it's been fascinating to watch and what we've learnt doing it together. And I think the teams are going to really appreciate the results that they're about to see. Now, as part of that, just a bit more explanation. So when Ishmael put everything together with all of the teams running, it did create a few things that we hadn't anticipated before this point. So when you have all of the cars running, obviously they're all going to finish at different times. When we ran a single car, it was great because when it reached the finishing point and got back to the target, we could just switch off the motor, everything, job done. But if we did that for the first car that or the first vehicle that gets back to the starting point, it would mean that all the others would be sort of marooned out on the track somewhere. So we had to find a way. I say we. Ishmael had to find a way of keeping the simulation running until all of the vehicles have got back to base. So what you're going to see is at certain times, the cars that have finished may misbehave a little bit because of the way that the physics model is working. This is really trying to replicate real life, and Ishmael's have to put in a few sort of tweaks just to make sure that all of the cars keep running until they get to their destination. So what that means, you'll see your device beautifully presented on the simulation. But what's driving it underneath is, do you remember the original Wally? Each has an invisible Wally underneath. And it's the invisible Wally that does the number crunching for us, but visually it's your device that sits over the top. So a couple of your teams, you may see that your device, the nose of it may just disappear into the wall a little bit, and it might look a little visually a little bit sort of unbelievable. But just to say that when that happens, don't worry, because the calculations are all based on the total distance that you travel. So it's not actually the visual that you see with it sort of perhaps just nosing into the wall and ghosting into the surroundings. So don't worry about that. So we have to make sure we complete a run. Now, one of the other things that we had to do for it to complete a run was to switch off the part of the frictional model when the early runners get back to base, which was absolutely fine until then we start putting the elevation and start sloping the lane up or down. So if you have no friction and it's a real physical model, you can imagine what happens. No friction means that the cars will then just start skidding off in whichever direction the slope is. So you will see some of that. So don't worry if you see your vehicle reach the finishing line and then suddenly start sliding backwards or forwards. Don't panic. That is just the model loitering on your design while it lets the others complete their run. So hopefully that makes sense. Also, the elevation caused some issues because we got you used to the idea that when these sort of driving simulators work from the beginning, they tend to drop the model into the virtual reality and off they go. That was great, but again, dropping them in onto a lane that was already sloped caused instabilities in the model, which would take too long to fix at this stage. So what happens is they drop on a level track, and then you'll see, if you look very carefully, you'll see that the elevation increases. All right, so we've got that. And also in some of the views, you'll see that some vector rays, which are just a representation of sort of velocity vectors, force vectors, and that kind of thing. So yeah, just if you see those, that's what those are representing. Okay, so the important thing is that every team is traveling exactly the same distance. Obviously, it finishes the clock when you reach back to the datum, and the energy scoring, the energy calculation summation is the accumulator is also stopped when it gets to the datum point. All right, so just bear that in mind. So everyone travels exactly the same distance. Final point, the lane to get all of the 8 devices on there is much wider. So the perspective, when we say it's running sort of 2 meters, it won't look like that compared to what you might have been used to with quite a long, narrow lane. It's just that we've made it much wider to accommodate all of the 8 vehicles. So without further ado, here are the ranges for the heat. So what's going to happen is I'm going to play three videos, and you will see each of them individually, all of the vehicles on there. So we're going to start with a short range of 1.8 meters and 0 degrees elevation, followed by the medium range, 2.75 meters and +2 degrees, which means that the lane is sloping upwards to the wall. And then we're going to go for almost the maximum distance of 3.95 meters and 0 elevation. So this is a bit where I'm a little bit nervous. We've been working hard to put these together. So let's see that everything is going to behave. So we've got a video set up to show you what's going to happen. So here we go. I might just skip backwards and forwards to remind you. So this is 1.8 meters and 0 degrees elevation. I'll play it a couple of times. So here we go. So you'll be able to identify your device. Oh, have we? It's paused, isn't it? Sorry, that was me. So you can see some of them escaping once they finish the run because of the frictional model. But don't worry, because it still tallies up all the scores correctly. And it's quite good fun if you can pan round when we're running this. You can see that the devices start falling off the end of the world, if you like. We're going to show you an example of what happens, the chaos that happens. So there we go. So if you want to, we just rerun so that you can catch it. And I'm going to present the scores at the end of the 3 heats. So this is on the short distance. You can see some teams have gone for lower mass and are very quick. Okay. So that was the short range. So congratulations, everybody completed it successfully within the time, and no issues. All of the vehicles behaved perfectly. So that was the short range. Now we're going to go to the medium range, 2.75 meters. This time the slight curveball is that the lane is going to start angling upwards. Okay, so you'll see that the let me just check I've got the right one. Yeah, so you'll see that the lane is going to angle up when it gets started. So let's see what happens here. And again, you can see that they're picking up speed because it's sloping back towards the datum. So the ones that finish will keep going. Top left, you can see that that's the one with the vector rays showing things like the if you look very closely, sometimes if we're running a single vehicle, you can see the load transfer from front to rear as it hits the wall and that kind of thing. So you can see that the physics is having an effect. Okay, so there we go. So that is the medium range, and off that one would go to infinity and beyond. So congratulations on that one. Let's go back, and then we will check. I'm just going to rerun that one again, just so you can follow. No doubt you're following your own devices. You may not be spotting the competitive element of it at the moment. Perhaps you're getting used to it and starting to see. You'll notice obviously some of the either the lighter devices or the very powerful devices are the ones that go charging off. So obviously they're going to do well on time, but it depends what happens. It's time and energy that is important. keep going, keep going. There we go. Back to back to the start. So final one is 0 elevation, and it's going to be 3.95. So this is the long range. Now visually it doesn't necessarily look like the long range because we've made the lane incredibly wide, but here we go. 3.95 meters, 0 degrees, 3, 2, 1, and away we go. So you got, I think that's is that Brunel with the angled wheels just escaping? Oh, we might get to see this one fall off the end of the world. Oh, it stayed. It stayed. Not going fast enough. There we go. So that's 3.95 meters. All right. So that is the that's the heats. So I'm going to show you the scores for the heats, and then we can work out who the finalists are going to be going through to the so the top 3 are going to go through to the final itself. Here we go. The virtual competition results, and the team is going through to the finals. So we can see the what's interesting is that the top 3 for the time is not the same as the top 3 for the energy. So low mass was not the ultimate the ultimate reason. So there's obviously a combination of mass of the device and also the motor and gearing and so on that you chose. So so there we have it. That's the scoring. So in for the time in the heats, we've got Hertfordshire were in first place. Second was UCLB, and third was Kingston 2. In the energy, we had UCLA was first, UCLB was second, and Kingston 2 was third. So what does that mean? Let's go forward to the finalists. So we're going to have when we combine those scores, the final is going to be between UCL A, UCL B, and Kingston Team 2. Okay, so that's where we've got to. All right, so happy with that. I feel like I'm just talking at a blank screen, but hopefully you've all taken that on board. So what we're going to do now is we're going to the top 3 teams, and are going to go through to the final, and they're going to be 3 individual elements again at a different combination of distance and elevation. So let's progress with that. So for the final, the ranges for the final are shown on the screen. So we've got a short distance with an elevation of 1 degree, medium at 2.545 meters with 0 degrees elevation, and then a real test, long range 3.3 meters, -5 degrees, which means it is going to be sloping down towards the wall. The trick will be, will your device actually reverse when it comes back in the other direction. Okay, so here we go. Finalists, are you ready? So I should point out that we have, so this is Kingston on the left. We've got the UCL B team in the middle and UCL A on the right-hand side of the lane. So 3, 2, 1, here we go. Let's hit the play button and see what happens. So all quite closely matched. All of them rushing off to infinity and beyond. Let's play that one again so you can just see. So we can see in terms of time, it was UCLB followed by Kingston, followed by UCLA. Okay, the next will be the medium. So it's level elevation 2.45 meters. So let's have a look at that one. So again, here we go. All of the teams lined up, ready to run. And again, it's level, so we'd expect them all to successfully complete. There we are. So again, same in terms of time. Obviously, we can't see the energy scores or visualize them as it's all happening, but it does tell a different story behind the scenes, which we'll catch up with when we've run the 3 finals. Let's just run that one again. Good. And now the final one. The test of 3.3 meters, but it is minus 5 degrees. So let's have a look at what's going to happen with this one. So here we go. Long range and 5 degrees. So you can see much quicker down. Again, UCLB whizzing along. And then if you look, this is where some of the physics model starts taking over so that we give it time for the others to catch up. So there we go, one more time. Third of the finals, and off we go. And again, congratulations, you all, with the 5 degree downslope, you all managed to achieve that. You might have noticed that Kingston nosed into the scenery a little bit when it hits the wall. That's because, relatively speaking, theirs is a slightly longer design. So there we go. Well done, teams. Congratulations on that. Just going to check what I've got coming up on the next slide, because I don't want to be going and giving any of the game away. So next we have, I think this is the slide that we called Wacky Races. So this is what can happen. We set one up just so you can see what happens if it all goes wrong. So I think this is quite a steep slope. So this isn't part of the competition, this is just a demonstration run, and if we leave it running long enough, you'll start to see that we get a few collisions and vehicles misbehaving themselves and things like that. So you can see we've got a couple of them starting to sit at a bit of an angle because of the way the physics, the engine is running. If you look towards the bullseye target, there we go. So those two bash into each other, and then that's it. That one's disappeared into the scenery. I'll just skip forward, see what happens as we get further down. Do we get any more misbehaving? Oh yeah, there we go. Look, so so they all start getting out of shape. So let's see what happens from this point. So it's interesting that even though this is a theoretical model, that they do get a bit of a sort of a y-axis component going and start drifting off sideways. Oh, there we go. So it's almost design challenge meets robot wars. Okay. Right, so that is the finals completed. So what's going to be happening next is we're going to take a well-earned break. We're a little bit over time, but we'll catch up on that with the prize giving. So let's all be back here for 12:40, I think, just so we grab 5 minutes out of the break, and we'll see you at 12:40 for the keynote speech, and then announcement of the winners and handing out the prizes. So see you shortly. So, hi everyone. Yellen, are you back?
I am.
Good, good. Okay. Do you want to lead it from this point?
Sure, happy to do so. So we are now back from the break. So I am passing on to Ben to do his keynote speech before we do the prize giving. Ben, the floor is yours.
Hello. Sorry, struggling with my mute button. Hello, everyone. It was a real pleasure to witness all of the designs in this competition. The standard was really, really high, so you should all be pretty proud of what you've achieved. I was going to give you a fairly brief keynote speech talking about my background and where I've come from, and then why I'm so interested in the design challenge as a competition. So I graduated from University College London in 1998, which is 23 years ago. Feels doesn't feel like that long ago, but there you go. And I got my first job working in motorsport for Mount-Tune race engines, where we designed the WRC engine for the late great Colin McRae's Ford Focus rally car. I was actually working for Tim Baker at the time. He wasn't a prof at the time, but he is now. So he got me my first foot in the door in the motorsport world. So I'll be grateful for that forever for him. Then I moved on to advanced engine research, also working for Tim, where I worked on a Le Mans car for MG, which was a great project, a clean sheet engine design. And then approximately 20 years ago, I joined Ilmor Race Engines, which has since become Mercedes AMG high performance powertrains. When I first joined Ilmor, I was working on the IndyCar engines, which is Indy Racing League, which are methanol powered engines, which is a fascinating fuel. Very high calorific value, sorry, very low calorific value and high latent heat of vaporization, meaning that you have to use an awful lot of it. And when you use it, it chills the air so much that you could actually get frost forming on the outside of the engine in certain places. So it was a very weird fuel to use, but I enjoyed working on that. The last 17 years of my career, I've been working in Formula One, which had always been my goal, really, ever since university or even since A-levels. And it's been an amazing experience. I've loved every minute of it. In Formula One, you get to use the skills that you learn on your engineering degrees. Innovation kind of has no limits in Formula One, is what I like to say to my engineers, that the only limit is your imagination. So if it makes the car go faster, then we'll permit you to do it. So it's something where you can truly explore the boundaries of physics and design parts to eke out that last millisecond. So the Formula One has been a big part of my life. The last 7 years have been particularly satisfying, where I've been able to be at a senior level in the engine design team, and Mercedes, as I'm sure some of you will know, have won the last 7 years on the trot, which has never been done before. So it was great to be part of that. And then, as Tim's already mentioned, I've actually now resigned from Mercedes, and I will soon join Red Bull Powertrain. So they are deciding to design their own powertrain and bring the whole chassis and power unit all under one roof. So that's enough about me. Why am I so interested in Design Challenge? Well, being an engineer was just an absolute fact that was going to happen to me. My dad was an engineer, my granddad was an engineer. It was just part of the conversation around every dinner table, and I really didn't want to get into a world where my engineering had boundaries, and I couldn't make something out of what was obviously the best material to make it out of because of price or because of availability. I wanted it to be completely about the purity of engineering, and what the parallel that I draw between the design challenge and motorsport is that you're given a set of rules to which you need to do the very best job you can to extract every last ounce of performance, and that's exactly what I've been doing in motorsport for over the years. So you have an idea, you do your fundamental engineering on it, you work out how that can make a difference to the performance that you're trying to achieve. In my world, it's all about milliseconds. In the design challenge, it's about accuracy, speed, and energy. So there's a balance between those three parameters that you need to try and maximize. But there are, in a Formula One engine, there's 25,000 parts that, although it's a large scale business, there are only 50 engineers that look after those 25,000 parts. So you can't work on everything and make them all optimum. So you have to decide what you need to work on. So you have to look at how much time and effort that you put into a piece and how much performance that you're likely to gain from it. So let's, for example, in the UCLA design where they had the optimized wheels, I did like that, but the question that was asked about exactly how much performance could you get out of those wheels was an interesting question, because if it was a very, very small value compared to spending that same amount of engineering effort in another area, then perhaps that engineering effort should have been spent in that other area. And so trying to correlate the effort that you put in versus the likely performance that you could yield is something that's an incredibly important part of trying to compete in an engineering sport. So what I would like is that all of you budding engineers that are taking part in this competition, you can see the analogy certainly into motorsport, but also, you know, all of engineering is competitive, but whether you're trying to compete in a marketplace or whether you're just trying to compete against physics and try and, you know, create the right amount of energy to power the vehicle of your choice in the smallest volume, smallest cost, smallest mass. It's you are competing against the physics, and having to work out how to do that is a really important part of being a good engineer. Because I studied in London, there was a few engineering graduates that decided to pursue a career outside of engineering in the city. They got lured by the financial sector or something like that. And it really depresses me every time I hear of an engineering graduate that succumbs to another career. Engineering truly is a really, really satisfying career. I think there's some studies done on the who make the happiest people and to what careers they pursue. I think number one is actually gardening, which I can completely understand. But right also at the top of the list is engineering, and I think it's because we're also creative, and anything that you can think of that you can then turn that idea into reality and actually make a difference, solving the many problems that there are in the world. And with the sustainability being such a big part of the future, working out how to solve that is exactly is exactly what is needed, and engineers are the ones that are going to do it. So I'm hoping that a competition like this can get your creative juices going, and that you can go out and pursue a career, not necessarily in motorsport, but if it is in motorsport, then you know who I am, so you can send your applications to me. But if it's not, you want to go out there and solve the world's problems, then great. I do hope that this competition has inspired you a little bit to do that. So thank you very much for taking part in it. I have found it really, really fascinating. There's some brilliant designs, the bar is really, really high this year, so that's great to see. So that's all from me, and thank you very much.
Thank you, Ben. Now I suggest that we start with the prize giving ceremony, and Ben, if you don't mind, beginning with the design award. I know you just switched off your cam. If you could come back, please.
I
Thank
did.
you.
Are we
Yeah.
gonna put on the
Hang on.
screen the PowerPoint?
Okay.
Yeah. Can you see it on the screen at the moment?
No.
No.
Can you not? Oh, okay.
No.
Right.
Just yet.
2 seconds. Can we do it in the slightly different order, Yelena? Just because otherwise I have to skip through slides and people might get a sneak peek of what's happening.
Okay, what's that order, Tim?
The one that we did when we mentioned it. No, it's poster first, poster competition. So it goes poster presentation.
Presentation design peer.
Yep, you've got it.
Okay, fine. Davide, would you mind starting them, please? And apologies for that.
Can you see the slides now?
Yes, I can. Thank you.
Yes, we can. Yeah.
Okay. So yeah, that's the order for the presentation. So poster first.
Hello, good afternoon, everybody. First of all, again, as for everybody, I've been impressed by the quality and the effort that you put in all your work. So to all the participants, the people that have reached the final, a massive thank you. It has been great for me to witness this. Please, if you have not received a prize, the prize is in being here with us today and having shared with your work that you submitted in a timely manner. So again, thank you ever so much for what you've done. So for the poster, we had 2 effectively with the same score at the number 1, and the second one very, very close will be classified as a position 3. So we'll start from the position 3 with a brief comment. The position 3 is the University of Hertfordshire. From a poster and the presentation of your work, the colors in the section have been used very, very carefully to highlight the different areas of the program. So well done. It is not common to find such a clear project presentation overall, so you could use this for your future. For the position number 1 in Durham, what we liked all together was that the presentation was clear, very readable, and the product was at the center of the poster. So you got your eye catched by the product that you were sharing, and at the same time, all the information were organized very, very nicely around it. A slightly different approach, but still of a high value added, is that UCLA has structured and organized the layout using clear colors that were not invasive, so it was everything clear to read, and all the information were there to look at. So overall, all these 3 examples, different philosophies, all of the 3 have achieved a very, very good result. You can use them for your future effectively guidelines when you want to do something like that. Again, thank you, everybody, and hope you enjoyed the competition so far.
Thank you, Davide. Tom, would you mind presenting the presentation award, please?
Oh, delighted. Thanks, Juliana. Presentations are interesting one, aren't they? Everyone, I think, hates giving presentations, but certainly in my experience, the only way to get good at giving presentations is to practice. So hopefully that you've valued this. I know it's all virtual, but my advice to you guys is get out there, put yourself forward, start giving presentations, because that's the only way to get better. So the order, can we go on one slide? So 3rd in the presentations, UCLA. We thought it was particularly good in the on the engineering behind the design and the detail, but when it came to questioning, I think not quite as good as the top 2 there. In 2nd place, we've got UCLB. The presentation overall was excellent, especially in the design process and how you did that. That was really good, and particularly enjoyed the final animation in that presentation, and the answers to the questions we thought was very good as well. And top of the shop there, Durham 1. Excellent overall. We gave you top marks for the visual aids and the quality of the presentation overall, and the answers to our questions we thought was pretty well done. So congratulations to all of them, all of you there, and I've really enjoyed the day. Thanks very much.
Thank you, Tom, and well done, teams. Next, Ben, if you wouldn't mind doing design.
Yes, of course. If we can just go on one slide then, please. Okay, so in third position is UCLB. That was a great, solid little design. I liked the fact that you actually made it and showed a video of that as well. That was great, yeah, neatly put together. The University of Hertfordshire, one of the few teams that really thought about the end float of all the wheels, so I really liked to see that. So thank you very much. That was some good work. And then the winners is UCLA. I thought that really was another level. The effort that you went to on every single component shows the sort of attention to detail that I asked my engineers to aspire to. So really well done for the effort on that. That was a great vehicle. I'd like to see it. Good work.
Thank you, Ben. Ishmael, are you here to do the peer review, please?
Yes.
Great, thank you.
Yep, so this is the part of the competition where you guys as the students have sort of made your pick and decided which teams and devices you thought were best. So coming in third here we have Durham 1, then in second we have the University of Hertfordshire, and then first place as well goes to UCLA. Thank you very much.
Thank you, Ishmael. Tim, will you be doing the virtual competition results?
Sure, yeah, I can announce the virtual competition winners. So there we go. So from the finalists, the virtual competition finalists, we have in terms of time, in third place UCLA, in second place Kingston 2, and in first place UCLB. And for the energy, we had in third place Kingston 2, in second place UCLB, and in first place UCLA. So that gives us the scores from the finalists. These are added to the heat scores as well, and then that gives us the overall totals for the competition as a whole. So what we can do now is we can, just checking my notes, we can now announce the winners. Just to explain, so what we did, we took you all through the overall event, and then we separate out for the overall winners of the Northeast region and then of the Greater London region for the teams that are going to go through to the national final. So with no further ado, for the Northeast, in second place we had Durham 1, and the winner for the Northeast region was Durham 2. So congratulations to both teams. Congratulations to Durham 2. You'll be going through to the national final. But also just to say, we've really enjoyed having you joining our competition in the Greater London region. You've been a really excellent addition, and enjoyed having you along. So congratulations to you. Next, we're going to move on to the Greater London region. Yelena, do you want me to announce that one as well? Or do you want to do that one?
Yeah, go ahead.
Okay, so moving forward to the Greater London region. So the competition winners for the Greater London region. So in third place, Kingston 2, in second place, UCLB, and first place, the winners, UCLA. So again, congratulations to all the teams. It was a very close competition. Also, just to explain, in real life, what happens is the final is always based on the physical competition, and as you saw in the regulations, we announced in consultation with all the universities, because this was going to be a virtual competition. These results are a result of the accumulation of points all the way through the competition. So every element has been added up. Yeah, very well done to all the teams. Congratulations to UCLA. On a personal note, this is the first year that I haven't been teaching the design challenge, so not sure if it's anything to do with things I've put in place in the years gone by, or my teaching was so poor that now that I've moved on, the standard has improved. But either way, I've really enjoyed to sort of watch the events unfold this year. A little bit more from a UCL perspective from the sidelines, but it's been yeah, as I say, overall the level of competition has been absolutely fantastic. And then just one final slide. I thought you'd also like to see the if we like the event order, and that is the 1, 2, 3 repeats the Greater London running order. So overall event winners for what we've just witnessed today: UCLA first, second UCLB, and in third place Kingston 2. But it was right the way across the board. I think it's probably one of the most competitive. All 8 teams, all really very close, especially going into the virtual finals. And just like the physical competition, that's really where it sort of separates the teams out, because obviously you get the 3 heats and then progress through to the final. But yeah, brilliant. Well done, everybody.
I second that. Congratulations, everybody. And I'll go into a little bit more detail at the end. I would pass on now to, oh, we're going to do a clapping. I would pass on now to my colleague Alex, who's going to say a couple of words before we do the closing ceremony. Alex, are you here? We are a little bit over time, so let me just double check whether Alex is here. Apologies, I don't believe Alex Turnbull, my colleague, is here, so we will move straight on to the closing ceremony. And Alex, if you are here and I've missed you, please jump in. Okay, I think it would be an understatement to say that this year and a bit has been challenging for all of us. Students of all ages, young people across the country have been impacted by the pandemic, as has your education. Despite so many challenges along the way, I'm very proud, and I think everybody is very proud of what we have managed to achieve today and today's event. I would like to start by thanking you, the students. I must admit that COVID and associated restrictions had the Design Challenge Steering Committee thinking on its feet at times. Despite spending a considerable amount of time on contingency planning, we were not sure how much you would be able to practically achieve in the given circumstances and what the level of engagement would be like. We have been genuinely impressed by your enthusiasm and continued resilience, and we believe that your results speak for themselves. You should be very proud of what you have achieved here today. I would like to thank our industry partners, Autodesk, Mercedes High Performance Powertrains, and IMechE. Quite simply, we couldn't do it without your support. Our sponsors do not just provide us with financial support, as you can see today, but get actively involved with the competition and provide key industry insight, which helps us maintain industry relevance and enables us to offer better opportunities for students and equip you better as you go into employment. I would like to thank Ben Hodgkinson and the entire Design Challenge Steering Committee for their hard work and dedication. In particular, the head of our technical committee and the GLR Design Challenge Regional Lead, Tim Baker. Since coming on board, Tim has been the driving force behind much of the innovation and developmental work across the Design Challenge. He has outdone himself this year and continues to work tirelessly on the competition, devoting many hours and days on the Design Challenge, always looking to improve the competition and ways in which we can drive it forward and get the best out of engineering students, for which we, and I personally, am most grateful. I would like to thank Ismail Ahmed from UCL for designing the Design Challenge app for the institution and for the support he has shown the IMechE Student Challenge portfolio across the years. Finally, I would like to thank Simon Paish, the IMechE GLR chair, who has been active behind the scenes as the vice chair of the challenge. He has played a key role in securing the correct governance structure for the challenge, which will in the long term ensure the future of the competition. I would like to close by saying that we'll be passing on links to feedback forms, as we do want to hear from you and continue to improve what we do. Well done to the GLR regional finalists, UCLA Team A. Well done to all of you, and I look forward to welcoming teams to the national finalists in October. Thank you very much, everybody.
Thank you very much, Jelena.
Thanks, Jelena. And just to say thanks for all of your support, because you've really helped to steer the Design Challenge over the last 18 months, and it's been a pleasure working with you.
Okay, thank you everybody, and we will share a recording of this once it's all branded and made to look pretty, and I hope you had a good time today. Thanks everyone, take care, bye bye.
Thank you very much, cheers, bye bye.